Quantum mechanics offers a world that feels vastly different from what we encounter in our everyday lives, a world that challenges our most fundamental sense of order and predictability. Unlike the classical physics of Newton, which thrives on definitive outcomes, on measurable certainties, on a universe that operates like a grand, predictable clockwork machine. The quantum realm is a world of probabilities, of uncertainties, and of strange, counterintuitive principles. At its very core lies the uncertainty principle, a profound and beautiful declaration that it is impossible to simultaneously determine the exact position and the exact momentum of any particle. This is not a limitation of our technology, not a fault in our methods of observation. It is an inherent, built-in property of nature itself. The principle, first introduced by the German physicist Werner Heisenberg, states that the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. It is a cosmic trade-off, a fundamental limit to our knowledge. This peculiar and beautiful truth reshapes our entire understanding of how particles move and interact. It forces us to abandon the dream of a perfectly predictable, deterministic universe, and to accept a reality where chance and randomness play an intrinsic, and perhaps even creative, role. The implications of this principle extend far beyond the simple act of measurement. They give rise to some of the most bizarre and wonderful concepts in all of science, including the idea of zero-point energy. This is a minimal, irreducible energy that remains in any physical system, even when it has been cooled to absolute zero, even when all its observable thermal energy seems to have been removed. In the classical world, cooling a system to absolute zero should bring all its constituent particles to a complete, perfect halt. But quantum mechanics forbids this. The energy that is tied to the inherent quantum motion of a particle can never be entirely eliminated. Even in their quietest, lowest energy states, particles are in a constant, jittery, and restless motion. This ceaseless behavior originates directly from the fundamental uncertainty in knowing both a particle's position and its momentum at the same time. These microscopic movements, often described as quantum jitters, are a reflection of the deep, ever-present, and dynamic activity that lies at the very heart of the quantum world. The energy that is associated with these ceaseless quantum fluctuations is not just a theoretical curiosity. It is a real physical phenomenon with measurable effects. It influences the behavior of systems in profound and often unexpected ways. For instance, the strange and wonderful properties of materials at extremely low temperatures, like superconductivity and superfluidity, are quantum phenomena that can only be understood by taking into account the effects of zero-point energy. The jittery, restless behavior of particles is not confined to the world of matter alone. It extends to the very fabric of empty space itself, what we perceive as a vacuum, what we intuitively think of as a perfect, absolute emptiness, is, in reality, a dynamic and vibrant stage, teeming with a hidden quantum activity. The classical notion of a vacuum as a completely empty, inert, and passive space is replaced in quantum mechanics by the concept of the quantum vacuum, a seething, energetic field that is filled with the fleeting, ghostly presence of virtual particles. This quantum vacuum is a realm of constant and spontaneous fluctuation, a place where pairs of virtual particles and their antimatter counterparts are constantly bubbling into existence, borrowing a tiny amount of energy from the vacuum for the briefest of moments before annihilating each other and disappearing back into the void. These particles are called virtual because they do not exist as stable, long-lived entities, but their fleeting presence has real and measurable effects. One of the most stunning and famous examples of this is the Casimir effect. If you take two uncharged, perfectly parallel metal plates and place them incredibly close to each other in a perfect vacuum, you will find that there is a small, but observable, attractive force pushing them together. This force is not gravity. It is not electromagnetism. It is the pressure of the quantum vacuum itself. The space between the plates can only accommodate virtual particles of certain, specific wavelengths. While the space outside the plates can accommodate all possible wavelengths, this creates a pressure differential, a net force that pushes the plates towards each other. It is a beautiful, tangible, and direct demonstration that even the emptiest of spaces are rich with a hidden and powerful quantum activity. This concept of vacuum energy, the energy that is inherent in the quantum fluctuations of empty space, is further developed and explained by the powerful framework of quantum field theory. In the classical view, a field, like an electric or magnetic field, is a smooth and continuous entity that fills space. But quantum field theory, which is the result of combining quantum mechanics with special relativity, reveals that these fields themselves are inherently restless, discrete, and jittery. At every single point in space, at every moment in time, these quantum fields are fluctuating, vibrating, and seething with a latent potential energy. And the fundamental particles of our universe are not, in this picture, solid, independent entities. They are the excitations of these underlying fields, the localized, quantized disturbances or ripples within them. An electron is not a tiny, solid ball moving through space. It is a localized vibration in the electron field. A photon is a ripple in the electromagnetic field. The vacuum, in this framework, is simply the ground state of these fields, the state of their lowest possible energy. But this ground state is not a state of zero energy. It is a state of constant, irreducible, zero-point fluctuation. This vacuum energy is not confined to a single, isolated location. It is a universal property of space-time, a cosmic energy field that spreads throughout the entire universe, influencing the behavior of all particles and all forces, on both the smallest, microscopic scales and the largest, cosmological scales. Its effects are not just limited to the strange quantum realm of our laboratories. They ripple outwards, shaping the very structure and destiny of the universe itself. The ceaseless, restless energy of the vacuum is now believed to be the driving force behind the accelerated expansion of the universe, the mysterious phenomenon that we attribute to dark energy. The fate of the cosmos, its journey into an ever-expanding and perhaps eternal future, may be dictated by the subtle, yet powerful, quantum jitters of empty space. The role of the uncertainty principle in defining this jittery, probabilistic, and deeply interconnected reality cannot be overstated. It is the foundational principle, the master rule, from which so much of the strangeness and the beauty of the quantum world emerges. The principle does more than just set a limit on the precision with which we can measure certain properties of a system. It dictates the very nature of quantum existence. It is the reason that particles can exist in a superposition of multiple states at the same time. The reason that the act of measurement can collapse a world of possibilities into a single actuality. The reason that particles can be entangled across vast cosmic distances. These phenomena, which so deeply defy our classical intuition, are all direct consequences of the fundamental trade-off, the inherent complementarity, that is at the heart of the uncertainty principle. And it is this same principle that governs the ceaseless, energetic dance of the quantum vacuum. Because the quantum fields that make up our reality must obey the uncertainty principle. They can never, ever be perfectly still. Even in the complete absence of any real, stable particles, The vacuum is alive with the constant, spontaneous creation and annihilation of virtual particles, a process that creates a baseline level of energy out of what appears to be nothing at all. This energy, this zero-point energy, though often imperceptible in our everyday lives, has profound and far-reaching implications. It is the energetic foundation that underpins the stability of the very atoms that make up our bodies. In the classical, pre-quantum picture of the atom, an electron orbiting a nucleus should, according to the laws of electromagnetism, constantly radiate away its energy and spiral into the nucleus in a fraction of a second. The fact that atoms are stable, that matter exists at all, was a deep and profound mystery. The uncertainty principle provides the solution. If an electron were to fall into the nucleus, its position would be very precisely known. But this would mean that its momentum would have to be incredibly uncertain, meaning it would have a huge and unpredictable velocity that would instantly kick it out of the nucleus. The electron is trapped in a stable orbit not by a classical force, but by a quantum mechanical compromise, a dynamic equilibrium between the electrostatic attraction of the nucleus and the inherent uncertainty-driven jitter of its own, quantum nature. The restless, jittery activity of the quantum vacuum, this constant hum of creation and annihilation, is not just an abstract, theoretical concept. It manifests in a host of real, tangible, and experimentally verified ways. Consider the Lamb shift, a tiny but measurable difference in the energy levels of the hydrogen atom. In the simple early models of quantum mechanics, two particular energy levels in the hydrogen atom should have been exactly the same, but precise. Spectroscopic measurements in the 1940s showed that they were, in fact, slightly different. This tiny discrepancy was a major puzzle, and its explanation provided one of the first and most powerful confirmations of the reality of the quantum vacuum. The Lamb shift is caused by the interaction of the electron in the hydrogen atom with the virtual particles of the surrounding vacuum. The constant jittery fluctuations of the vacuum fields effectively smear out the position of the electron, slightly changing its interaction with the proton and shifting its energy levels. It is a direct, measurable consequence of the electron feeling the ceaseless, energetic dance of the void. Similarly, the quantum vacuum is crucial in explaining the phenomenon of spontaneous emission, the process by which an excited atom can spontaneously emit a photon of light and transition to a lower energy state. In the classical world, an excited atom would just stay excited forever unless it was perturbed by an external force. But in the quantum world, the zero-point fluctuations of the electromagnetic vacuum are always present, providing a constant, subtle perturbation that can stimulate the atom to decay and emit a photon. The stability of molecular bonds, the very foundation of chemistry and of life itself, is also deeply connected to the properties of the quantum vacuum. The forces that hold atoms together in a molecule are not just the simple electrostatic forces of classical physics. They are a complex quantum mechanical dance that is mediated by the exchange of virtual photons, a dance that takes place on the stage of the energetic, fluctuating vacuum. The concept of vacuum energy also raises profound and tantalizing questions about the very origins and the ultimate fate of our universe. Quantum field theory, in its current form, suggests that the energy density of the vacuum is not a fixed, static property, but is something that can evolve over time, influenced by the expansion of the universe and the dynamics of the underlying quantum fields. This perspective ties the smallest, most fundamental scales of quantum mechanics to the grandest, most cosmological questions we can ask. It bridges the gap between the micro and the macro, suggesting that the same jittery quantum restlessness that governs the behavior of a single atom is also the force that is driving the destiny of the entire cosmos. The jittery, fluctuating nature of the quantum fields also provides a new and more profound way to understand the deep, and often mysterious, interconnectedness of all things. In the classical worldview, the universe is a collection of separate, independent objects, interacting through local forces. But the quantum worldview, and particularly quantum field theory, paints a very different picture. At every single point in space, at every moment in time, all the quantum fields, the electron field, the photon field, the quark fields, the Higgs field are present, are active, are fluctuating, are interacting. There is no such thing as a truly isolated system. The behavior of a single particle is not just determined by its own intrinsic properties. It is influenced by the state of all the quantum fields that span the entire universe. The vacuum itself is a dynamic, ever-changing, and deeply interdependent entity. This perspective challenges our classical notions of separateness and locality, replacing them with a vision of reality as a single, holistic, and deeply entangled system. Through the lens of quantum mechanics, the universe appears not as a collection of things, but as a network of relationships, a seamless, interconnected tapestry of interwoven forces and energies. And the zero-point energy, the ceaseless, restless hum of the quantum vacuum, is the energetic thread from which this entire tapestry is woven. It is the source of all potential, the ground of all being, the silent, invisible, and endlessly creative engine of the cosmos. Quantum mechanics, in the end, does not provide us with all the answers. In fact, it often leaves us with more questions and deeper mysteries than we started with. But it does open the door to a new and more profound understanding of the universe's intricate, dynamic, and restless nature. It invites us to see the world not as a static, finished product, but as an ongoing, creative process, a universe that is constantly being born, moment by moment, from the beautiful, strange, and endlessly fascinating jitter of the quantum void. The quantum vacuum, this seething, energetic sea that underlies all of reality, is not just a theoretical curiosity. It exerts a real, tangible, and often profound influence on the physical world. The effects of the vacuum's incessant. Quantum fluctuations are not confined to the esoteric realm of high-energy physics. They are woven into the very fabric of our existence, from the stability of the atoms that make up our bodies to the grand, cosmological forces that shape the destiny of the universe. One of the most striking and direct demonstrations of the vacuum's power is its influence on the stability of matter itself. In the classical, pre-quantum picture of the atom, the orbiting electrons should, according to the laws of electromagnetism, constantly radiate away their energy and spiral into the nucleus in a fraction of a second. The fact that atoms are stable, that matter as we know it can exist at all, was a deep and profound mystery. The solution lies in the strange, jittery dance of the quantum world. The electrons in an atom are not tiny planets orbiting a central sun. They are probability waves, and they can only exist in specific, quantized energy levels. The lowest of these levels, the ground state, is not a state of zero energy or perfect stillness. It is a dynamic equilibrium, a state where the electron is constantly interacting with the zero-point fluctuations of the surrounding quantum vacuum. It is this incessant quantum jitter, this constant exchange of virtual photons with the vacuum, that prevents the electron from falling into the nucleus. The stability of the atom is not a static property. It is an active, dynamic process, a delicate balance between the electrostatic pull of the nucleus and the energetic push of the void. The vacuum is not just a passive stage. It is an active participant in the very constitution of matter. The influence of the quantum vacuum extends far beyond the scale of a single atom. It offers a new and deeper understanding of the fundamental forces that operate on the grand, cosmic scales of the universe. In the context of Einstein's general theory of relativity, the energy density of the vacuum contributes to the overall curvature of space-time, the very geometry that governs the motion of galaxies and the expansion of the cosmos. This provides a deep and beautiful connection between the microscopic world of quantum fluctuations and the macroscopic world of gravitational interactions. As we have seen, the leading hypothesis for the mysterious dark energy that is driving the accelerated expansion of our universe is that it is the macroscopic manifestation of the vacuum's own intrinsic zero-point energy. This is a breathtaking idea. It suggests that the same jittery quantum fields that are responsible for the subtle behavior of a single subatomic particle are also the primary engine shaping the long-term evolution and the ultimate fate of the entire universe. The implications are profound. It means that the destiny of the cosmos is not just being written by the visible matter and energy that we can see, but by the invisible, and far more abundant, energy of the emptiness itself. This insight bridges the gap between the very small and the incomprehensibly vast, offering a new and more unified vision of how the universe operates. But the influence of the vacuum is not just about expansion. Theoretical models suggest that the same quantum fluctuations that are driving the universe apart today may have played a crucial role in the very formation of its structure in the first place. During the period of cosmic inflation, the tiny microscopic fluctuations in the quantum fields of the early universe would have been stretched to astronomical scales, creating the seeds of density variation that would later, under the influence of gravity, grow into the vast cosmic web of galaxies and clusters that we see today. The grand, intricate architecture of the cosmos is, in this sense, a frozen, macroscopic snapshot of the primordial quantum jitter. The uncertainty principle, as we have seen, lies at the very heart of these quantum connections. It is the master rule that shapes the behavior of all quantum systems, from a single particle to the entire universe. It is not just a limit on what we can know. It is a fundamental statement about the nature of existence. By enforcing a minimum, irreducible level of activity, even in the complete absence of any real particles, the uncertainty principle ensures that the vacuum is never truly empty, that it is always a source of dynamic, creative energy. This has profound consequences. It is this dynamic nature of the vacuum that is reflected in phenomena like the spontaneous emission of light from an excited atom. In the classical world, an atom in an excited state would simply stay there forever unless it was perturbed by an external force. But in the quantum world, the constant zero-point fluctuations of the electromagnetic vacuum are always present, providing a subtle but ever-present kick that can stimulate the atom to decay and to release a photon. It is the jitter of the void that makes the universe a luminous and not a darkened place. The uncertainty principle also sheds new light on the origin of the universe's fundamental constants, the parameters that govern our reality, the strength of the fundamental forces. The masses of the elementary particles are not, in our current theories, fixed by any deep underlying principle. They are numbers that we must measure, but in a deeper, more complete theory. These constants may not be arbitrary. They may be emergent properties, determined by the complex, self-consistent interactions of all the quantum fields within the vacuum. The constants have the values they do because they are part of a stable, self-consistent quantum reality. A reality that is constantly being shaped and sustained by the restless, jittery dance of the void. This connection between the fundamental properties of nature and the dynamics of the quantum vacuum reveals a deep and beautiful interdependence, a picture where the smallest scales of reality influence the largest, and where the most fundamental constants of nature are not just static numbers, but are the dynamic result of the universe's own Ongoing quantum activity. While the vacuum is often described as empty, this description is a profound misnomer that masks its true and deeply complex nature. At the quantum level, what appears as emptiness is, in fact, a seething, vibrant arena of ceaseless possibility. Virtual particles, these ghostly, fleeting entities, are constantly emerging from the void and interacting with each other before vanishing back into the nothingness from which they came. This contributes to a constant background level of energy, a vacuum energy that, while incredibly subtle, has profound and far-reaching implications for our understanding of the universe's origin, its evolution, and its ultimate fate. The observed, accelerated expansion of the cosmos, the phenomenon we attribute to the mysterious dark energy, is the most dramatic and large-scale manifestation of this vacuum energy. If this connection holds, it would mean that the same jittery quantum vacuum that governs the behavior of the subatomic world is also the cosmic engine that is determining the long-term trajectory of the entire universe. Quantum field theory provides the mathematical framework that allows us to understand these strange and beautiful dynamics. It extends the principles of quantum mechanics from individual particles to the continuous, all-pervading fields that are the true, fundamental constituents of reality. In this picture, the classical notion of a smooth, continuous field is replaced by a quantum field that is inherently discrete, probabilistic, and fluctuating. These fluctuations are not random, chaotic noise. They are governed by the precise and elegant rules of quantum mechanics. And at every single point in space, at every moment in time, these fields are rippling with a latent, potential energy, creating particles not as independent, solid entities, but as localized, quantized disturbances within the field itself. This paradigm shift, from a universe of particles to a universe of fields, transforms our entire understanding of matter, of energy, and of the forces that govern them. It offers a single, coherent, and beautiful framework that can unite the seemingly separate realms of particles and fields into a single, unified reality. The quantum vacuum also plays a pivotal and often underappreciated role in the emergence of the fundamental forces of nature. The electromagnetic force, for example, which governs the interactions of charged particles, arises from the exchange of virtual photons, the quantum excitations of the electromagnetic field. These virtual photons are constantly bubbling up from the vacuum, mediating the force between charged particles and then disappearing back into the void. The same fundamental principle applies to the strong and the weak nuclear forces, which govern the behavior of atomic nuclei. The forces of nature are not static properties. They are dynamic, quantum processes, a constant, ongoing conversation between particles and the vacuum. Even gravity, which we traditionally view through the classical geometric lens of Einstein's general relativity, is now understood to interact with the quantum vacuum. The search for a theory of quantum gravity is, in many ways, a search for an understanding of how the jittery, fluctuating nature of the quantum world can be reconciled with the smooth, continuous curvature of space-time. One of the most striking and creative consequences of the vacuum's energy is its role in the phenomenon of spontaneous symmetry breaking in the incredibly hot and dense conditions of the early universe. It is thought that the four fundamental forces of nature were unified into a single, symmetric superforce. As the universe expanded and cooled, the quantum fields that mediate these forces underwent a series of phase transitions, similar to the way that water freezes into ice. In these transitions, the initial, perfect symmetry was broken, giving rise to the distinct and seemingly separate forces that we see in the universe today. The jittery, restless, and dynamic nature of the quantum vacuum, with its constant activity, is what drives these symmetry-breaking events. Without this process, the universe might have remained a featureless, symmetric, and ultimately lifeless expanse. It is the breaking of the perfect symmetry of the initial state that gives rise to the rich, complex, and beautifully diverse universe we inhabit. The uncertainty principle, as we have seen, is the ultimate source of this cosmic creativity by enforcing a fundamental and irreducible limit on what can be known and measured. It ensures that the quantum world remains a dynamic, probabilistic, and interconnected system. It is a principle that is not merely a restriction on our knowledge, but is a source of the very phenomena that make the quantum realm so strange and so wonderful. It is the reason for the dual, wave-particle nature of matter. It is the source of the probabilistic outcomes of our measurements. And it is the engine behind the ceaseless, energetic fluctuations of the quantum fields and the vacuum energy. Through this lens, the uncertainty principle emerges not as a barrier to our understanding, but as a gateway to a deeper, more profound appreciation of the intricate, dynamic, and endlessly restless nature of reality itself. It is the universe's way of ensuring that there will always be more to discover, more to wonder at, more to explore. And it is a reminder that the world we live in is not a static, finished product, but an ongoing, creative, and beautiful dance between the known and the unknown, between certainty and possibility, between the particle and the wave. The universe is vast, mysterious, and, in a way that is both beautiful and deeply puzzling, seems to be surprisingly well suited for the existence of life. This observation, the fact that the fundamental laws and constants of nature appear to be exquisitely fine-tuned to allow for the emergence of complex structures, of stars, of planets, and of conscious observers like ourselves, has led scientists and philosophers to explore a fascinating and controversial concept known as the anthropic principle. In its essence, the anthropic principle proposes that the reason we observe a universe with these specific, life-friendly properties is because, if the properties were any different, we would not be here to observe them. Imagine a universe where the force of gravity was just a little bit stronger. Stars would burn through their fuel much more quickly, and would likely collapse into black holes long before complex life could have a chance to evolve on any orbiting planets. If gravity were just a little bit weaker, matter would never have clumped together to form stars and galaxies in the first place. The universe would be a cold, diffuse, and lifeless soup of gas. The same delicate balance applies to a host of other physical constants. The strength of the nuclear force, the mass of the electron, the value of the cosmological constant, all of these seem to be sitting in a very narrow and very special range of values that allows for the existence of a universe that is both stable enough and complex enough to support life. The anthropic principle offers a potential explanation for this apparent cosmic coincidence. It shifts the focus from asking why the universe is so perfectly balanced to simply acknowledging that our own existence as observers is a powerful form of selection bias. We are, by definition, living in a universe that is capable of producing us. This idea has sparked a great deal of debate and reflection. Some see it as a profound insight into the nature of our relationship with the cosmos, a recognition that we are not separate from the universe we observe, but are an integral and significant part of it. Others view it as a mere tautology, a statement that is true by definition, but which lacks any real explanatory power. This debate is brought into sharp focus by the concept of a designer. The apparent purposeful design of the universe has long been used as an argument for the existence of a divine creator. But the anthropic principle offers a potential, naturalistic alternative. The argument for design without a designer, is perhaps best illustrated by the process of biological evolution. The intricate complexity and apparent design of a living organism, like the human eye, was once seen as irrefutable evidence for a divine watchmaker. But Charles Darwin's theory of evolution by natural selection showed how this complexity could arise gradually, through a long and completely natural process of random mutation and non-random selection. In the same way, the fine-tuning of the universe may not require a cosmic designer. Instead, it could be the result of a similar cosmic scale process of selection. The most popular and well-developed version of this idea is the multiverse. If our universe is just one of a vast, and possibly infinite, number of other universes, each with its own randomly assigned set of physical laws and constants, then the fine-tuning problem dissolves. It is no longer a miracle that we find ourselves in a life-friendly universe. It is a statistical inevitability. We are simply the lucky winners of a cosmic lottery of unimaginable proportions. This cosmic landscape, a term that comes from string theory, which predicts a vast number of possible vacuum states, each corresponding to a different set of physical laws, provides a concrete, physical mechanism for generating the ensemble of universes that the anthropic principle requires. The idea of a designer is appealing because it offers a simple and emotionally satisfying explanation for the complexity we see around us. But it is an explanation that ultimately leads to an infinite regress. If the universe was designed by a creator, then who or what designed the creator? The multiverse, on the other hand, offers a potential scientific explanation that is grounded in the known, or at least plausible, laws of physics, without the need to invoke a supernatural entity. The anthropic principle also forces us to confront the deep philosophical implications of our own existence. If life is a rare and special outcome of the universe's physical laws, a fortunate roll of the cosmic dice in a vast and mostly sterile multiverse, what does that say about our place in the cosmos? For some, this perspective can be a source of humility, a reminder of the incredible fragility and preciousness of our own conscious existence. It can foster a sense of responsibility, a recognition that we are the custodians of a rare and beautiful cosmic experiment. For others, however, it can feel diminishing. It can lead to a sense of cosmic loneliness, of our lives being devoid of any grand cosmic purpose, the universe. In this view, does not care about us, it simply is. The meaning of our lives is not something that is given to us by the cosmos. It is something that we must create for ourselves, in the face of a vast and ultimately indifferent reality. This existentialist perspective is a powerful and challenging one, and it is a direct consequence of taking the implications of modern cosmology seriously. The anthropic principle also touches on the very nature of scientific inquiry itself. It is a principle that is not, in the traditional sense, falsifiable. We can never, even in principle, observe the other lifeless universes in the multiverse. This has led some to argue that the anthropic principle is not a true scientific explanation, but a philosophical one. But others argue that this is too narrow a view of science. A good scientific theory is not just one that makes testable predictions. It is also one that provides a deep, coherent, and satisfying explanation for the world we see. And the anthropic principle, when combined with the multiverse, does provide a potential and deeply compelling explanation for one of the most profound and otherwise inexplicable features of our universe, its hospitality to life. The debate over the anthropic principle is a debate that is likely to continue for a long time. It is a debate that is not just about the laws of physics, but about the nature of explanation, the limits of science, and the very meaning of our own human existence. And as we continue to probe the universe, to refine our theories, and to push the boundaries of our knowledge, we are not just learning more about the cosmos, we are also learning more about ourselves, about the remarkable, and perhaps even necessary, conditions that have allowed for the emergence of a conscious, questioning, and meaning-seeking being in the midst of a vast and beautifully fine-tuned cosmic mystery. For centuries, scientists have been on a quest to understand the universe, from its smallest particles to its largest structures. Thanks to remarkable advancements in technology and groundbreaking experiments, we are now able to peer into the farthest reaches of space and time, uncovering insights that were once beyond our wildest dreams. Some of the most intriguing, and also most perplexing, of these discoveries have come from the study of dark energy, of cosmic inflation, of the energy of the vacuum, and of the tantalizing, if speculative, possibility of a multiverse. These are concepts that are not just reshaping our understanding of the universe. They are providing evidence that challenges our most long-held assumptions and is inviting us to think about the cosmos in new and often counterintuitive ways. What if the universe is not as simple or as singular as we once thought? What if the things we cannot see, the forces we do not yet understand, play a much larger and more fundamental role in shaping reality than we ever imagined? These are the kinds of profound and exciting questions that are driving the frontiers of modern cosmology. One of the greatest of these frontiers is the mystery of dark energy. In the late 20th century, astronomers made a discovery that shook the very foundations of cosmology. By observing distant Type Ia supernovae, they found that the expansion of the universe is not slowing down, as had been expected due to the mutual gravitational pull of all the matter in the cosmos. Instead, the expansion is accelerating. This implied the existence of a mysterious, repulsive force, a form of dark energy that is pushing space-time apart. This dark energy is now thought to make up roughly 70% of the total energy density of the universe, making it the dominant component of our cosmos. But what is it? And how do we study something that we cannot directly see? The answer lies in studying its effects. The light from those distant supernovae, which act as standard candles with a known intrinsic brightness, allows us to measure the expansion history of the universe with incredible precision. And these measurements have consistently confirmed the presence of an accelerating expansion. Another powerful tool is the study of the cosmic microwave background, the faint afterglow of the Big Bang. The detailed patterns of temperature fluctuations in the CMB provide a snapshot of the universe when it was just a few 100,000 years old. And by analyzing these patterns, cosmologists can infer the total amount of dark energy in the universe and how it has influenced the growth of cosmic structure over time. These two independent lines of evidence from the late universe and the early universe both point to the same startling conclusion: our universe is dominated by a strange, invisible, and repulsive form of energy that is driving it towards an ever-accelerating future. The discovery of cosmic acceleration has given a new impetus to another, equally profound idea in cosmology: the theory of cosmic inflation, first proposed in the 1980s by the physicist Alan Guth. Inflation is the idea that the universe underwent a brief, but incredibly powerful, period of exponential expansion in the very first moments after the Big Bang. This rapid, hyper-accelerated growth would have stretched the fabric of space-time, smoothing out any initial irregularities and setting the stage for the large, flat, and uniform universe that we observe today. The theory of inflation is a beautiful and elegant one, and it solves a number of the deep conceptual puzzles of the standard Big Bang model. It also provides a natural mechanism for generating the initial density fluctuations that would later grow into the galaxies and large-scale structures we see today. But what is perhaps most fascinating about the theory of inflation is that it doesn't just explain the state of our current universe. It also provides insight into the very mechanisms that shaped its birth, The inflationary paradigm suggests that our universe may have been born from a tiny quantum fluctuation in a pre-existing high-energy vacuum state. It provides a framework for understanding why the universe is so vast, so old, and so structured in the way that it is. And the theory has been remarkably successful. Its predictions confirmed with stunning precision by our observations of the cosmic microwave background. As we continue to study the universe, we are constantly refining our understanding of this inflationary epoch. Some believe that inflation could have lasted for a much longer period than initially thought, or that it could have occurred in multiple distinct phases. And as we have seen, the idea of eternal inflation suggests that our universe may be just one of a vast and constantly growing number of pocket universes, each with its own unique properties. This brings us to the concept of vacuum energy, another key and deeply mysterious element of modern cosmological research. Vacuum energy is a form of energy that is thought to exist even in the perfect vacuum of empty space, where there is no matter or radiation. It arises from the constant quantum fluctuations that are an inherent feature of the quantum world. These fluctuations, where virtual particles pop in and out of existence, give rise to a baseline level of energy that fills all of space. And while this vacuum energy might sound like a subtle, abstract concept, its effects are anything but. In fact, many physicists believe that the vacuum energy of space is the physical reality behind the mysterious dark energy that is driving the accelerated expansion of the universe. As the universe expands, the amount of vacuum energy increases, contributing to the repulsive force that is pushing galaxies further and further apart. The connection between vacuum energy and dark energy is still a subject of intense research and debate. But it is clear that understanding the nature of the vacuum is crucial for understanding the fundamental forces that are at play in our cosmos. Looking towards the future, one of the most exciting and also most challenging areas of cosmological research involves the development of new telescopes and experiments that are designed to probe the very limits of our understanding, and perhaps even to test the speculative but deeply compelling hypothesis of the multiverse. The multiverse, as we have seen, is the theoretical concept that our universe may be just one of many, each with its own set of physical laws and constants. While the idea of a multiverse is still highly speculative and may forever lie beyond the realm of direct experimental verification, advances in technology and cosmology are bringing us closer to a point where we might be able to search for indirect circumstantial evidence. Future telescopes, like the now operational James Webb Space Telescope, are providing us with more detailed and more precise observations of distant galaxies, of exoplanets, and of the early universe than ever before. This data is allowing us to test our cosmological models with unprecedented accuracy, and to search for any subtle anomalies that might hint at new, undiscovered physics. If the multiverse hypothesis has any basis in reality, it is possible that we might one day detect the faint telltale signs of other universes, perhaps in the form of specific, non-random patterns in the cosmic microwave background, or in the discovery of anomalies in the fundamental constants of nature that could suggest the influence of other parallel realities. While this is still a long way from becoming a reality, the very potential for such a discovery is what drives the scientific quest forward. As our experiments and our telescopes continue to evolve, we may soon be able to answer some of the most profound and long-standing questions about the nature of the universe and our place within it. The field of cosmology is in a state of rapid and exciting evolution. The discovery of dark energy has shown us that our universe is a far stranger and more mysterious place than we ever imagined. The theory of cosmic inflation has provided us with a powerful and elegant framework for understanding its origins. And the ongoing study of vacuum energy is offering new and often puzzling, clues into the fundamental forces that are shaping its destiny. As we continue to push the boundaries of our knowledge, one thing is clear: the universe is far more complex, more beautiful, and more wonderfully mysterious than we ever dreamed. And the discoveries we make in the coming years will continue to challenge, to inspire, and to expand our understanding of the grand cosmic story in which we all play a small, but not insignificant, part. The debate surrounding the anthropic principle and its connection to the concept of a multiverse stands as one of the most contentious and also most thought-provoking issues in contemporary physics and cosmology. At its heart, it is a debate about the very nature of scientific explanation and about the limits of what we can ever hope to know about the universe. On the one hand, we have the startling and seemingly undeniable fact of our own existence. We live in a universe that appears to be exquisitely and improbably fine-tuned to allow for the emergence of complexity, of life, and of conscious observers. The fundamental constants of nature, the strength of gravity, the charge of the electron, the value of the cosmological constant all seem to be sitting in a very narrow and very special range of values. A slight tweak in any one of them, and the universe as we know it would not exist. The anthropic principle, in its weak form, simply acknowledges this as a form of selection bias. Of course, we find ourselves in a life-friendly universe. We could not have found ourselves anywhere else. This is illogical, but not particularly deep. Explanation: the strong version of the principle, which suggests that the universe must have properties that allow for life, veers into the realm of metaphysics and teleology. But the weak anthropic principle finds a powerful and scientifically respectable partner in the theory of the multiverse. If there are a vast, and perhaps infinite, number of other universes, each with its own, randomly assigned set of physical laws and constants, then the fine-tuning of our own universe is no longer a miracle. It is a statistical inevitability. We are simply living in one of the rare, habitable oases in a vast and mostly sterile cosmic desert. This is a powerful, and for many, a deeply satisfying explanation. But it is an explanation that comes with a heavy philosophical price. It requires us to accept the existence of a potentially infinite number of unobservable realities, a concept that many find to be a violation of the principle of scientific parsimony. This tension between the empirical and the theoretical, between what we can observe and what we can infer, highlights an ongoing and often passionate philosophical debate about the very boundaries of science itself. Critics of the multiverse and the anthropic principle argue that they are not true scientific theories. A scientific theory, in the traditional Popperian view, must be falsifiable. It must make risky, testable predictions that, if they are not borne out by experiment, would force us to abandon the theory. But the multiverse, by its very definition, seems to be unfalsifiable. We can never travel to another bubble universe to check if its physical laws are different. And so, for the critics, the multiverse is not science. It is a form of recreational mathematics, a philosophical or metaphysical speculation that is dressed up in the language of physics. Supporters of the multiverse, on the other hand, argue that this is too narrow and too rigid a view of what constitutes science. They point out that the theories from which the multiverse arises, like cosmic inflation and string theory, are themselves, in principle, testable. Inflation, for example, makes specific predictions about the statistical properties of the cosmic microwave background, predictions that have been stunningly confirmed. And while string theory has not yet made a unique, testable prediction, it is a rich and ongoing research program that could one day do so. The multiverse, in this view, is a logical, and perhaps even unavoidable, consequence of our best and most successful physical theories. To reject the multiverse simply because it is not directly observable would be to reject the very theories that have been so successful in explaining the universe we can see. This debate highlights a deep and often unspoken tension within the scientific community itself. There is a constant interplay between the drive for empirical verification and the pull of theoretical elegance and explanatory power. When scientists explore the fine-tuning of the universe, they are not just doing physics, they are engaging with questions that have traditionally been the domain of metaphysics, of philosophy, of theology. They are asking questions about existence, about necessity, about the ultimate causes of reality. Does this integration enrich scientific inquiry, or does it dilute its empirical rigor? Can metaphysical perspectives offer meaningful insights into the deep questions of cosmology, or do they risk overstepping into a realm of untestable and ultimately unscientific? Speculation. There is no easy answer to these questions. They point to the complex and often blurry boundary between science and philosophy, a boundary that is constantly being negotiated and redrawn as our knowledge evolves. The study of the fine-tuning of the universe and the possibility of a multiverse also brings a host of ethical considerations into sharp focus. The pursuit of these ideas requires a vast investment of public resources, the construction of massive particle accelerators, the launching of sophisticated space telescopes, the funding of generations of theoretical physicists. This raises important questions about scientific priorities. In a world with so many pressing, practical challenges, from climate change and disease to poverty and conflict, is it ethically justifiable to spend billions of dollars on the pursuit of knowledge that may be purely abstract and may never have any direct, practical application? Critics would argue that these resources could be better spent on research that has a more immediate and tangible benefit to humanity. Proponents, on the other hand, would argue that the pursuit of fundamental knowledge is one of the highest and most noble of all human endeavors. It is an expression of our deepest curiosity, our desire to understand our place in the cosmos. And history has shown, again and again, that breakthroughs in fundamental science, even those that seem purely abstract at the time, often lead to unexpected and revolutionary practical applications. The development of quantum mechanics, for example, was driven by a pure, intellectual curiosity about the nature of the atom. But it has led directly to the technologies of the digital age, from the transistor and the laser to the MRI machine and the GPS. The ethical implications of these debates also extend to the very content of the theories themselves. The idea that our universe is just one of a vast and mostly sterile multiverse, and that our own existence is a mere statistical accident, can be a deeply unsettling one. It can challenge long-held religious and philosophical beliefs about the specialness of humanity, about the existence of a cosmic purpose, about the very meaning of our lives. Scientists have a responsibility to communicate these ideas with care, with nuance, and with a deep sensitivity to their potential, cultural and psychological impact. They must be clear about what is established, scientific fact, and what is speculative, theoretical possibility. The dialogue between science and the broader culture is a crucial one, and it is one that requires a sense of mutual respect and intellectual honesty from all sides. The ongoing debate over the anthropic principle, the multiverse, and the fine-tuning of the cosmos is a vibrant and healthy one. It is a sign of a science that is grappling with its own deepest and most profound questions. It is pushing the very boundaries of what we consider to be empirical inquiry, and it is forcing us to engage in a new and more sophisticated dialogue between physics, philosophy, and ethics. The disagreement between those who see the universe as a unique and perhaps necessary creation and those who see it as a random and fortunate accident is a reflection of a deep and enduring tension in human thought. It is the tension between the search for a single, unifying explanation and the acceptance of a vast and perhaps incomprehensible diversity. As we continue to explore the universe, to refine our theories, and to push the limits of our observational capabilities, we may one day find evidence that will tip the scales in one direction or the other. Or we may find that the answer is something far stranger and far more beautiful than we can currently imagine. But whatever the outcome, the very process of engaging with these questions, of daring to ask about the ultimate nature of reality, is a process that enriches our understanding, deepens our sense of wonder, and ultimately elevates the human spirit. The cosmological constant is one of the most enigmatic and also most powerful concepts in all of modern physics. It is a single number, a simple term in Einstein's equations of general relativity, but it is a number that seems to hold the key to the ultimate destiny of our universe. The story of the cosmological constant is a dramatic one, a tale of rejection, of redemption, and of deep and still unresolved mystery. Albert Einstein first introduced the cosmological constant into his theory in 1917. At the time, the prevailing view was that the universe was static, eternal, and unchanging. But Einstein's own equations of general relativity seemed to predict a dynamic universe, one that should either be expanding or contracting under the influence of gravity. To reconcile his theory with the prevailing cosmological wisdom, Einstein added a new term to his equations, a fudge factor that represented a kind of cosmic anti-gravity, a repulsive force inherent in the fabric of space-time itself that would perfectly balance the attractive force of gravity and allow for a static universe. But this static universe turned out to be unstable, and more importantly, it turned out to be wrong. In the 1920s, the American astronomer Edwin Hubble, through his meticulous observations of distant galaxies, made the revolutionary discovery that the universe is not static. It is expanding. The galaxies are all moving away from each other, and the further away they are, the faster they are receding. Upon hearing of Hubble's discovery, Einstein is said to have abandoned his cosmological constant, calling it his biggest blunder. For decades, the cosmological constant was relegated to the dustbin of scientific history, a curious footnote in the story of general relativity. But in a stunning and beautiful twist of fate, the blunder was resurrected in the late 20th century by studying distant Type Ia supernova. Astronomers found that the expansion of the universe is not just continuing, it is accelerating. This implied the existence of a mysterious, repulsive force, a dark energy that is pushing the cosmos apart, and the simplest and most natural mathematical representation for this dark energy is Einstein's old and once reviled cosmological constant. The cosmological constant, in its modern interpretation, is thought to be the physical manifestation of the vacuum energy, the zero-point energy of the quantum fields that permeate all of space. As we have seen, the quantum vacuum is not an empty nothingness, but a seething, energetic sea of virtual particles. And this energy, according to general relativity, has a gravitational effect. A constant vacuum energy density would exert a strong, negative pressure, a repulsive force that would drive the accelerated expansion of the universe. This is a beautifully elegant and unifying idea. It connects the strange, microscopic world of quantum fluctuations with the grand, macroscopic dynamics of the cosmos. But it also leads to one of the most profound and embarrassing problems in all of theoretical physics, the vacuum catastrophe. When physicists try to calculate the expected value of the vacuum energy based on the principles of quantum field theory, they get a number that is astronomically, absurdly large. It is about 120 orders of magnitude, a 1, followed by 120 zeros larger than the observed value of the cosmological constant that is needed to explain the cosmic acceleration. This is so as without a doubt the single worst theoretical prediction in the entire history of science. It is a sign that there is something deep and fundamentally wrong with our current understanding of the relationship between quantum mechanics and gravity. Why is the observed energy of the vacuum so incredibly, exquisitely small compared to the theoretical prediction? This is the cosmological constant problem, and it is a puzzle that has haunted physicists for decades. If the vacuum energy were as large as the theory suggests, the universe would have been torn apart in the first fraction of a second of its existence. The fact that we live in a universe that is both long-lived and capable of forming complex structures like galaxies and stars means that there must be some unknown and incredibly precise mechanism that is canceling out almost all of the vacuum energy, leaving just the tiny residual amount that we observe as dark energy. The fine-tuning of the cosmological constant is so extreme that it has led many physicists to embrace the anthropic principle and the idea of a multiverse. If there are a vast number of other universes, each with its own randomly determined value for the cosmological constant, then it is no surprise that we find ourselves in one of the rare universes where this value is small enough to allow for our own existence. In this cosmic landscape of possibilities, we are the winners of an almost impossibly unlikely cosmic lottery. But this is an explanation that many find to be deeply unsatisfying. It is a retreat from the traditional goal of physics, which is to find a unique and necessary explanation for the properties of our universe. The cosmological constant problem also highlights the deep and as yet unresolved connections between the quantum world and the world of general relativity. The cosmological constant is the point where these two great theories meet, and it is the point where they seem to be in most violent conflict. The resolution of this problem will almost certainly require a full, and as yet undiscovered, theory of quantum gravity, a theory that can consistently describe the quantum nature of space-time itself. But the cosmological constant is not just a theoretical puzzle. It is a key determinant of the ultimate fate of our universe. If the dark energy it represents is truly constant, then the universe will continue to expand at an accelerating rate forever. The galaxies will recede from each other, the sky will grow dark, and the universe will end in a cold, lonely, big freeze. If, on the other hand, the dark energy is not a constant, but a dynamic field that could change its value over time, then other, more dramatic fates are possible, including a big rip where the very fabric of space-time is torn apart. The cosmological constant is a single, simple number, but it is a number that contains within it some of the deepest and most profound mysteries of the cosmos. It is a window into the strange, energetic nature of the void. It is a key to understanding the past, the present, and the ultimate future of our universe. And it is a stark and humbling reminder of the vast, uncharted territory that still lies at the very frontier of our scientific understanding. The future of our quest to understand the universe is a story of ever-advancing technology, of ever-deepening theoretical insight, and of an unquenchable and uniquely human curiosity. We are living in a golden age of cosmology, a time when new discoveries are being made at an unprecedented rate, and when we are poised to answer some of the longest-standing and most profound questions about our cosmic origins. The next generation of telescopes and experiments, both on the ground and in space, will push the boundaries of our knowledge into new and previously inaccessible realms. The James Webb Space Telescope is already giving us our first stunning glimpses of the cosmic dawn, the era when the very first stars and galaxies lit up the universe. In the coming years, it will continue to map this ancient frontier, to study the formation and evolution of the first cosmic structures, and to search for the chemical fingerprints of life in the atmospheres of distant exoplanets. On the ground, massive. New 30-meter class optical telescopes will provide a powerful synergy with Webb, allowing for detailed, high-resolution follow-up studies of the most interesting objects it discovers. The search for the nature of dark matter and dark energy, the two great invisible components of our universe, will enter a new era of precision. The Vera C. Rubin Observatory in Chile will conduct a decade-long legacy survey of space and time, creating a deep, multicolor movie of the southern sky. Its vast trove of data will allow cosmologists to map the distribution of dark matter through weak gravitational lensing on an unprecedented scale, and to trace the history of cosmic expansion with thousands of new supernovae, providing the most stringent tests yet of the nature of dark energy. The European Space Agency's Euclid mission will provide a complementary, high-resolution view from space, mapping the shapes and redshifts of billions of galaxies to create a three-dimensional map of the cosmic web. And deep underground, in heavily shielded laboratories, a new generation of highly sensitive detectors will continue the direct search for the elusive dark matter particle, hoping to catch the faint, rare signal of a dark matter particle interacting with an atom of ordinary matter. But perhaps the most exciting new frontier in cosmology is the dawn of gravitational wave astronomy. Since the first historic detection of gravitational waves in 2015 by the LIGO Observatory, we have opened a completely new window onto the universe, a window that allows us to hear the cosmos, not just see it. The current network of ground-based detectors is constantly being upgraded, increasing its sensitivity and allowing us to detect the faint ripples in spacetime from the mergers of black holes and neutron stars at ever greater distances. But the ultimate goal is to take gravitational wave astronomy into space. The Laser Interferometer Space Antenna, a planned mission for the 2030s, will consist of 3 spacecraft flying in a triangular formation, separated by millions of kilometers. LISA will be a gravitational wave observatory of truly cosmic proportions, sensitive to the low-frequency gravitational waves that are inaccessible from the ground. It will be able to detect the mergers of supermassive black holes at the centers of distant galaxies, providing a new way to study the coevolution of galaxies and their central black holes. And most excitingly of all, LISA may be sensitive enough to detect the faint, stochastic background of primordial gravitational waves that are predicted to have been generated during the period of cosmic inflation in the first fraction of a second after the Big Bang. The detection of these primordial gravitational waves would be a monumental discovery, a smoking gun confirmation of inflation, and a direct glimpse into the physics of the universe at energies that are 1 trillion times higher than anything we can achieve in our terrestrial particle accelerators. It would be a window into the very moment of creation. Alongside these remarkable observational advances, the theoretical quest will continue. The search for a unified theory of quantum gravity, the holy grail of modern physics, will be guided and constrained by these new, precise data. Advances in string theory, in loop quantum gravity, and in other, more speculative, approaches may lead to a breakthrough in our understanding of the fundamental nature of space, of time, and of reality itself. And the rapidly developing field of quantum computing may one day provide us with a new and incredibly powerful tool for simulating the complex quantum dynamics of the early universe, allowing us to test our theories in a new virtual laboratory. Despite all these remarkable and ever-advancing tools and theories, it is possible, and perhaps even likely, that some of the deepest questions about the origin and nature of the universe will forever remain beyond our grasp. There are fundamental, built-in limits to what we can know. The cosmic horizon limits how far we can see. The Planck scale may represent a fundamental limit to the resolution with which we can probe the fabric of reality. And the multiverse, if it exists, may be forever beyond the reach of direct experimental verification. These limitations are not a sign of failure. They are a reminder of our own human finitude, a call to a sense of intellectual humility. They bring us back to the great, timeless, philosophical questions that have animated the human spirit since its inception. Why is there something rather than nothing? Does the universe have a purpose? What is the nature of consciousness? And what is our place in the grand, cosmic scheme of things? Science can illuminate many aspects of these questions. It can push back the boundaries of our ignorance. It can reveal the deep and beautiful order of the natural world. It can provide us with a powerful and coherent story of our cosmic origins. But it may not be able to provide the final, ultimate answers. Some dimensions of these questions may always remain in the realm of philosophy, of art, of religion, of personal, subjective experience. And this is not a weakness. It is a strength. It is a recognition of the richness and the complexity of the human quest for meaning, a quest that is not reducible to a single scientific framework. We end, then, where we began, with a sense of profound and beautiful awe at a universe that is both deeply comprehensible and endlessly mysterious. With each new discovery, the island of our knowledge grows, but so does the shoreline of our ignorance. As you lie in the quiet of the night, on the peaceful threshold of sleep, you can feel a sense of participation in this grand human adventure. The very consciousness that is listening to these words, that is contemplating the origin of the cosmos, is a part of that cosmos, a part of the universe that has, through a long and improbable evolutionary journey, woken up and begun to ask questions about itself. The atoms in your body were forged in the hearts of long-vanished stars. The energy that powers your thoughts is part of the same cosmic flow that drives the galaxies. And your consciousness, whatever its ultimate nature may be, is one of the most remarkable and most beautiful phenomena in a universe that was born from a seeming nothingness to come to know itself. Good night, and may your dreams be as vast, as mysterious, and as wonderful as the cosmos that is your home. We build rockets, sending probes to the farthest corners of our solar system. We gaze deep into space with telescopes that can reveal the faint, ancient light of galaxies billions of light years away. Our technology is powerful, a testament to the relentless reach of the human mind. Our curiosity is boundless, an insatiable hunger to understand the grand, the cosmic stage upon which our fleeting lives unfold. And yet, for all our progress, for all our ambition, there are places we can never reach. There are realms so distant, so fundamentally inaccessible, that they will forever remain a mystery, shrouded in the darkness of the ultimate unknown. These are the forbidden zones of the universe, regions of reality that are lost to us, not because of a failure of our technology, but because of the very nature of the cosmos itself. Some of these forbidden realms are being actively created right now, as we speak, torn from our view by the relentless and accelerating expansion of the cosmos. Entire galaxies, once our cosmic neighbors, are receding from us at speeds faster than the speed of light, slipping silently and irrevocably beyond the horizon of what is possible for us to ever see or to touch. Others of these forbidden zones are buried deep within the most extreme and violent objects in the universe, in the hearts of black holes. Their event horizons are not just boundaries, they are one-way membranes in the fabric of space-time, a point of no return that seals away whatever falls inside, its secrets, its information, its very existence, forever erased from our view. And some of these forbidden realms exist not in space, but in time. The very first moments of the universe's creation, the fiery crucible of the Big Bang, are hidden from us behind a veil of such extreme heat and density that no telescope, no theory, no future breakthrough will ever be able to pierce it. And yet, we wonder, we imagine, we reach with our minds where our bodies and our machines can never go. Could those distant, unreachable galaxies, forever cut off from us by the expanding void, harbor their own unique forms of life, their own civilizations, forever living in their own isolated cosmic island? Forever unaware of our existence, do the dark, silent hearts of black holes conceal the deep, fundamental secrets of the nature of reality itself? The answers to the puzzle of quantum gravity is the true story of the birth of time, of the very beginning of our universe, locked away behind an impenetrable and eternal cosmic curtain. The forbidden zones of the universe are a profound and humbling reminder of our own inherent limits, but they are also a powerful and beautiful testament to our greatest strength, our curiosity. Even in the face of the unreachable, of the unknowable, of the eternal mystery, we continue to ask, to explore, to dream, and perhaps, in doing so, in the very act of reaching for what lies beyond our grasp, we find something just as profound and just as meaningful as the answers we seek. The universe is vast, far vaster than our human eyes, or even our most powerful and sophisticated telescopes, can ever hope to see when we gaze up at the clear, dark expanse of the night sky. We are not just looking out into space, we are looking back in time. The light from the nearest stars has traveled for years to reach us. The light from the Andromeda galaxy, our closest major galactic neighbor, has been on its journey for over 2.5 million years. And the faint, distant smudges of light from the most remote galaxies have been traveling towards us for billions of years, carrying with them a ghostly image of the universe in its infancy. But there is a limit, a fundamental and absolute boundary to our vision. There is a cosmic horizon, a spherical shell around us, beyond which we can never see, never explore, and never reach. This is the cosmic censorship zone, the vast and perhaps infinite region of the cosmos that exists beyond the confines of our observable universe, a realm where reality itself becomes, for us, forever unknowable. Our observable universe, the part of the cosmos from which light has had time to reach us since the Big Bang, stretches out for about 46 billion light-years in all directions. This number might seem strange. If the universe is only 13.8 billion years old, shouldn't we only be able to see objects that are at most 13.8 billion light-years away? The reason we can see farther is because the very fabric of space itself has been expanding throughout the entire history of the universe. The distant galaxies that emitted the light we see today were much closer to us when that light began its long journey. But in the billions of years that it has taken for that light to travel to us, the space between us and those galaxies has been stretching, carrying them much farther away. This expansion of space also stretches the wavelength of the light itself, a phenomenon known as cosmic redshift. The light from the most distant galaxies is so severely redshifted that it has been stretched from the visible and ultraviolet parts of the spectrum all the way into the infrared and microwave regions, which is why we need specialized telescopes like the James Webb Space Telescope to see it. But there is a profound and deeply unsettling problem with this cosmic expansion. It is not slowing down, as one might expect due to the mutual gravitational pull of all the matter in the universe. It is accelerating, driven by a mysterious and still completely unexplained, repulsive force known as dark energy. The universe is not just growing, it is growing at an ever-increasing rate. This has a dramatic and inescapable consequence. As time passes, more and more of the distant galaxies are being pushed away from us so fast that they will eventually cross our cosmic event horizon. They will be receding from us at a speed that is faster than the speed of light itself. This does not violate Einstein's theory of relativity, as it is space itself that is expanding, not the galaxies moving through space. But it does mean that any light emitted by those galaxies after they cross this horizon will never be able to reach us. They will be, in a very real sense, causally disconnected from our future. Anything that is currently beyond 46 billion light-years from us is already forever lost. And the galaxies that are currently on the edge of our observable universe will one by one follow them into the darkness, their light fading from our view, their existence erased from our cosmic reality. This is not a temporary technological problem. It is a fundamental, physical limit. Even if humanity one day masters the art of interstellar, or even intergalactic travel, even if we create spacecraft that can approach the speed of light, we will still never be able to reach these hidden, forbidden regions. The very laws of physics, the relentless, accelerating expansion of space-time itself, prevent us. This leads to one of the most profound and most tantalizing questions in all of cosmology: what lies beyond the observable universe? The simplest and most conservative answer is based on the cosmological principle, the assumption that our corner of the universe is not special, and that on the largest scales, the cosmos is homogeneous and isotropic, meaning it looks roughly the same everywhere and in all directions. If this is the case, then the universe beyond our view is likely just more of the same. An endless, and perhaps infinite, expanse of space filled with the same kinds of galaxies, stars, and planets, all governed by the same universal laws of physics. In this picture, the universe beyond our horizon is not fundamentally different from our own. It is just forever inaccessible. But there are other, more exotic and more mind-bending possibilities. Some cosmologists, working on the frontiers of theoretical physics, suggest that beyond our observable universe, the very nature of reality might be different. If the Big Bang was not a single, unique event, but was just one of many in a larger, eternal inflation process, then the universe beyond our sight could be a vast and chaotic multiverse. There could be other bubble universes, each with its own unique set of physical laws, fundamental constants, and even different numbers of dimensions. These would be separate, parallel pockets of reality, forever cut off from our own, each one a different and perhaps wildly different answer to the question of what a universe can be. The question of whether our own universe is finite or infinite also has a profound bearing on what might lie beyond our horizon. If the universe is truly spatially infinite, as the current data seems to suggest, then the consequences are staggering. In an infinite universe, every possible arrangement of particles, every possible configuration of matter and energy must, by statistical necessity, repeat itself an infinite number of times. This means that somewhere out there, far, far beyond the cosmic censorship zone, there is another Earth, another you, an almost identical copy, living out an almost identical life, perhaps making just one tiny, different choice at this very moment. And there are an infinite number of such doppelgangers, spread out across an infinite cosmic tapestry. If, on the other hand, the universe is finite, then it might have a strange and wonderful topology, wrapping around on itself in a higher dimension. In such a universe, if you were to travel far enough in one direction, you might eventually end up right back where you started, like an ancient mariner circumnavigating the surface of a spherical Earth. And then there is the most radical and least likely possibility that beyond our universe, there is simply nothing, a true absolute void, a region where even space and time themselves cease to exist. This idea, however, contradicts much of what we have learned from quantum mechanics, which suggests that even the emptiest of space is a seething, energetic sea of quantum fluctuations. What makes the cosmic censorship zone so eerie and so philosophically profound is that we will likely never know for sure what lies beyond it. And as the universe continues its accelerating expansion, the region of space that we can access, the volume of our observable universe, is, in a relative sense, shrinking. The galaxies that we can see today, the most distant quasars and the most ancient protogalaxies, will eventually fade from our view, their light stretched by the expanding space into an undetectable, infinite redshift. Billions, and then trillions, of years from now. Future observers in our own local group of galaxies will look up at a sky that is almost completely dark, empty, and devoid of the rich cosmic tapestry that we are privileged to still be able to see. The grand cosmic web of galaxies will have vanished into the darkness, leaving only a small, lonely, and gravitationally bound island of stars in an infinite and seemingly empty void. The knowledge that we have so painstakingly acquired, the knowledge that we live in a vast, expanding cosmos filled with billions of other galaxies, could one day be lost, buried in the digital archives of a long-forgotten history, with no way for a future civilization to ever independently verify it. And yet, even within these profound and humbling limitations, our universe holds endless mysteries. The cosmic censorship zone is not just a physical boundary, it is a philosophical one. It is a stark and powerful reminder of the inherent limits of human knowledge. It tells us that no matter how far we look, no matter how powerful our instruments become, there will always be something just beyond our reach, some deeper and perhaps ultimate truth that we can never fully grasp. It is the final and most absolute cosmic horizon, a frontier that can never be crossed, not because we lack the technology or the will, but because the very nature of our expanding and accelerating. Reality ensures that some of its deepest secrets will forever remain hidden from our view. This is a humbling realization. We are used to thinking of science as a powerful and perhaps even omnipotent tool. A tool that can, in principle, unlock all the mysteries of the universe. But the very nature of the cosmos itself seems to be telling us that some answers will always and forever be out of our reach. This does not mean that we should stop searching. On the contrary, it makes our quest for knowledge all the more precious, all the more urgent. Every moment that we have to study the cosmos, every single photon of ancient light that we can gather, is a fleeting and irreplaceable opportunity to piece together the story of our universe before it moves, forever beyond our grasp. In the end, the cosmic censorship zone is not just a physical limit, it is an existential one. It forces us to confront our own, small, and temporary place in an endless and endlessly shifting reality. It reminds us that there will always be things we cannot know, places we cannot visit, and mysteries we cannot solve. But perhaps, in the end, that is what makes the journey of exploration so beautiful and so profoundly human. The universe is not a puzzle for us to solve, but a poem for us to wonder at, a story for us to participate in, even as its most distant and most ancient chapters are slowly and inexorably drifting further and further away from our reach. The universe is a time machine. This is not a poetic metaphor. It is a literal, physical fact. Every time we look up at the night sky, we are not seeing the cosmos as it is in our present moment, but as it was in a distant and often ancient past. The farther away a galaxy is, the longer its light has taken to travel to us. And therefore, the further back in time we are looking. The light from some of the most distant galaxies has been journeying towards us for billions of years. carrying with it a ghostly, and often beautiful, image of the universe in its infancy. And here lies one of the most haunting and most profound truths about our cosmos. Some of the galaxies that we observe in the night sky, some of the very objects that we are studying with our most powerful telescopes, no longer exist. They are phantoms, cosmic ghosts, whose last dying light is only just now reaching our shores, while they themselves have already vanished. Their substance scattered, their stars extinguished, their reality dissolved into the expanding void. This eerie and deeply counterintuitive phenomenon is a direct consequence of the universe's rapid and accelerating expansion. The very fabric of space itself is stretching, and it is carrying the distant galaxies along with it, pushing them ever farther apart. For the galaxies that are relatively close to us, in our own local cosmic neighborhood, this expansion is a slow and gentle process. But for the galaxies that lie at the extreme, outer edges of our observable universe, the expansion is happening so quickly that they are, in effect, being pulled out of our reality. Their light struggling against a cosmic current that is flowing faster than the speed of light itself. This means that while we can still see the light that they emitted billions of years ago, a message from their distant past, they themselves have already crossed our cosmic event horizon, the point of no return, the boundary beyond which no new information, not a single additional photon of light, can ever reach us again. To truly grasp this strange and wonderful idea, imagine you are standing on the shore of a vast ocean, watching a boat sail away towards the horizon. As it moves farther and farther away, it will eventually reach a point where it seems to disappear from your view, not because it has ceased to exist, but because the curvature of the Earth has carried it beyond the limit of your sight. Now, replace the ocean with the expanding fabric of space, and the boat with an entire galaxy. The universe is stretching so rapidly that certain very distant galaxies have already been carried beyond our cosmic horizon, never to be seen again in their present state. Their ancient light is still traveling towards us, a long and fading echo from their past. But once that final ancient light has all arrived, no more will follow. They will fade from our view, not because they have become too dim, but because they have become too distant, their light forever trapped in a space-time that is expanding too fast for it to ever reach us again. The most astonishing and most humbling aspect of this phenomenon is that there are galaxies we can see today, right now, in the images from our most powerful telescopes that have, in all likelihood, already ceased to exist in any recognizable form. Some of them may have been swallowed by supermassive black holes. Others might have been torn apart in colossal galactic collisions, and many have simply been stretched out into a thin, cold, and featureless nothingness by the relentless and accelerating expansion of space. The beautiful spiral arms, the glittering, star-forming nebulae, the vast, ordered structures that we see in these ancient images, all of this is long gone. The light that we receive from them today is their final message, their last beautiful glimpse into a vibrant existence before they vanished forever from the stage of the cosmos. One of the most famous and iconic images in the history of astronomy, the Hubble Deep Field, is a perfect illustration of this. This single, long exposure image captured the light of thousands of distant, and therefore ancient, galaxies in a tiny, seemingly empty, patch of the night sky. Many of these galaxies are so far away that their light has been traveling for over 10 billion years to reach us. We are seeing them as they were when the universe was in its infancy, just a few 100 million years old. And yet, they are no longer there. The specific cosmic structures that they formed, the individual stars that they contained, and perhaps even the planets and the potential life that may have orbited within them. All of this is gone, washed away by the relentless cosmic tide of time and expansion. But their light, like a faint, beautiful echo from a long-forgotten past, is only just now reaching us, allowing us to witness them as they were, frozen forever in a single, ancient moment of time. This is a concept that is deeply difficult for our minds to wrap themselves around, because in our everyday terrestrial experience, things do not just disappear like this. When we look at an object, a tree, or a house, we have a very strong and reliable intuition that it exists, here and now, in our present moment. But the universe, on its grandest scales, does not work that way. The farther away something is, the older the image we see of it. And for the most extremely distant galaxies, we are looking so far back in time that their present state is not just unknown to us, it is, in a very real sense, unknowable. Some of them may still exist, in some transformed and evolved form, but many, many others are simply gone. Their matter dispersed, their energy absorbed, their story concluded in the vast, silent expanse of space. What makes this cosmic vanishing act even more unsettling is that the universe's accelerating expansion is, as far as we know, an irreversible process. The galaxies that are currently teetering on the very edge of our observable universe today will, one by one, soon be lost to us forever. We will still be able to see their ancient, fading light for a while, for perhaps millions or even billions of years to come. But that light, that final ghostly message from their past, will eventually stop arriving. They will fade into a final, absolute blackness. Not because they have been destroyed in a fiery cataclysm, but because the fundamental laws of physics, the very geometry of our expanding space-time, will have made it impossible for their photons to ever reach us again. The fabric of space will have stretched so much and so quickly that they will have been, in effect, completely and irrevocably erased from our reality. This means that, in a very real sense, we are living in a golden age of cosmic observation, right now, at this specific and perhaps fleeting moment in cosmic history. We have the technology to look deep into space and to see the beautiful, ghostly remnants of these ancient phantom galaxies. But in the far, far future, observers in our own galaxy will look up at a much, much lonelier universe. The distant galaxies that we marvel at today will no longer be visible. The Milky Way and its small, gravitationally bound group of neighboring galaxies will be all that remains in sight. And future astronomers, future civilizations, might never even know that the billions of other galaxies that we can still see ever existed. The record of their existence will have been lost, their light no longer able to reach us, their story erased by the expanding void. But this does not mean that these phantom galaxies are meaningless. Even though they have disappeared from the present-day universe, their ancient, ghostly light tells us a story, a crucial and irreplaceable story of the early cosmos. A story of how the first stars and galaxies formed from the primordial soup of the Big Bang. A story of how the intricate, beautiful, and complex structures of the universe evolved over billions of years. Every single ancient photon that reaches the mirror of our telescopes is a precious message from the past, a faint, beautiful whisper from a galaxy that may have been long, long gone. And these photons are precious because they allow us to piece together the history of our universe, before that history itself is lost to the inexorable forward march of time. There is also a profound and deeply human philosophical question that is hidden within this strange cosmic reality. If we see something, but it no longer exists, did it ever really exist in the way that we intuitively understand existence? When we look at a galaxy that is 10 billion light-years away, we are seeing it as it was 10 billion years ago. But if we could somehow, magically, teleport ourselves to that location in space, right now, in our present moment, we would, in all likelihood, find nothing. The stars would be gone. The beautiful spiral structures would have changed beyond all recognition. We would be staring into an empty, dark space, or at something entirely different from what we had expected. This profound disconnect between the past image and the present reality challenges our very understanding of what the now really means. In a universe where time and space are so deeply and inextricably connected, it also raises another, equally unsettling question. How much of our own universe, our own cosmic neighborhood, has already disappeared from the view of a distant, alien observer? Just as we see the ancient, ghostly images of galaxies that no longer exist, it is entirely possible that there are other civilizations, in other distant parts of the cosmos, that are, at this very moment, looking back at our own Milky Way, but seeing it as it was billions of years ago. To them, our galaxy, our sun, our Earth, might be nothing more than a faint, ancient glimmer of light from a time long past, a beautiful and poignant relic of a universe that has already moved on without us. One day, we too, in all our complexity and our beauty, may become a phantom, a galaxy whose ancient light continues to travel outwards into the expanding void, a message in a bottle cast into a cosmic ocean. Long after we ourselves have faded from existence, the universe is a vast and endlessly mysterious place. And the phantom galaxies that haunt the lenses of our telescopes are a powerful and beautiful reminder that nothing is permanent. Everything we see, everything we know, everything we are, is temporary, a fleeting, flickering moment in the grand, and often tragic, sweep of cosmic history. And yet, in that fleeting moment, there is a profound and undeniable beauty. The very knowledge that we are witnessing something that no longer exists, something that has been lost to the relentless, cosmic tide, makes every image, every observation, every single precious photon of ancient light all the more meaningful. It reminds us that the universe is always changing, always evolving, and that we are incredibly, wonderfully, and perhaps even tragically, lucky to be here, now, to glimpse even the tiniest fraction of its magnificent and ultimately fleeting story, before it, too, fades forever, beyond our reach. The universe hides its deepest and strangest mysteries in the darkness. And among the most enigmatic of these dark mysteries is the idea of primordial black holes, hypothetical and ghostly, remnants from the very first, fiery moments after the Big Bang. If they exist, they are not like the black holes we know, the stellar mass behemoths that are formed from the violent, explosive deaths of massive stars. These would be something entirely different, something more ancient, more fundamental, more elusive. They would be black holes formed not from the collapse of pre-existing matter, but from the raw, untamed, and incredibly dense energy fluctuations of the newborn universe itself. But here lies the profound and deeply frustrating paradox of their existence if they are real. They are so small, so dark, and so perfectly hidden in the vast, expanding fabric of space that we may never, ever be able to find them. Primordial black holes are believed to have formed in the very first, infinitesimal fractions of a second after the universe came into existence. At that time, the cosmos was an unimaginably hot and dense place, a chaotic, roiling sea of pure energy and fundamental particles. In this primordial soup, Tiny, random, quantum fluctuations slight and unavoidable. Imbalances in the density of energy could have been so extreme that they caused certain super-dense regions of space to spontaneously collapse in on themselves, forming minuscule black holes. Unlike the black holes that are formed from the collapse of dying stars, which must have a mass of at least a few times that of our Sun, these primordial black holes could, in theory, have any mass. They could be as small as a single atom, or as massive as a large planet, their size depending entirely on the scale and the intensity of the density fluctuation from which they were born. Theoretically, these ancient primordial black holes could have survived for the entire 14 billion-year history of the universe, drifting silently and invisibly through the cosmos. Perfect, dark relics of the first moment of creation. But their very nature, their small size and their lack of any significant interaction with their surroundings makes them nearly impossible to detect. Unlike the stellar mass or supermassive black holes that we can observe, which are often surrounded by bright, glowing accretion disks of gas and dust that is being pulled into them, these primordial black holes would be, for the most part, completely isolated, wandering through the vast, empty voids of the universe like silent, cosmic ghosts. If they are small enough, they would slowly emit a faint thermal radiation, a process known as Hawking radiation, and would, over immense cosmological timescales, eventually evaporate completely. But if they are just a little larger, say with the mass of a small asteroid, they could persist indefinitely, their existence completely invisible to our current and perhaps any future technology. For decades, scientists have been searching for any evidence, however indirect, of these ancient, primordial black holes, but finding them is like looking for a single dark grain of sand in an infinite dark desert. They do not emit any detectable light. They do not interact with their surroundings in any obvious way. And they may be far too small to have any significant gravitational influence on the stars and galaxies around them. The only real hope of detecting them lies in their potential. Gravitational effects. They could, in theory, act as gravitational lenses, their tiny but intense gravity bending the light of a distant star as they pass in front of it, creating a brief and characteristic brightening event. Or they could subtly affect the movement of the large-scale cosmic structures that we can observe. But even these potential clues are incredibly faint, almost imperceptibly so, when set against the vast and often noisy backdrop of the cosmos. One of the most intriguing and most exciting ideas about primordial black holes is that they could be a leading candidate for the mysterious and still completely unidentified dark matter, the invisible gravitational substance that seems to make up the vast majority of the matter in the universe. Dark matter is known to us only through its gravitational influence. It has weight, it pulls on galaxies, it shapes the large-scale structure of the cosmos, but it emits no light, no radiation, no signal of any kind. Could it be that this hidden gravitational mass that has eluded scientists for so long is, in fact, a vast cosmic population of ancient primordial black holes? Some researchers believe that this is a real and even a likely possibility, but there is, as yet, no direct experimental evidence to support it. If primordial black holes are indeed the source of dark matter, then they are even more elusive and more profoundly mysterious than we ever imagined. They would be everywhere, all around us, making up the very gravitational scaffolding of our own galaxy. And yet, they would remain completely and utterly unseen. The frustrating and beautiful reality is that even if they do exist, we may never be able to definitively prove it. They are too small to be observed directly. They are too dark to emit any detectable radiation. And they are too isolated to reveal themselves through their interactions with the world we can see. Even our most advanced telescopes and our most sensitive gravitational wave detectors may not be enough to ever confirm their presence. We might only ever be able to infer their existence from a collection of subtle, indirect clues, a slight, unexplained anomaly in the motion of a distant galaxy, a brief and unrepeatable flash of lensed light from a background star, a tiny and statistically ambiguous distortion in the faint, ancient glow of the cosmic microwave background. There is a cruel and beautiful irony in this. The very nature of primordial black holes, their ancient origin and their profound physical simplicity, makes them one of the most compelling and most elegant ideas in all of modern physics. And yet, at the very same time, it may place them forever beyond the reach of our direct, empirical verification. They could be everywhere, hidden in the silent, dark void of space. And yet, we might never be able to prove that they are real. The universe, it seems, does not always reveal its secrets easily, some of its deepest and most fundamental. Questions may remain forever unanswered, not because they have no answers, but because the answers are too well and too perfectly hidden for us to ever find them. And yet, the possibility of primordial black holes, the dream of finding these ancient cosmic relics, continues to haunt us, to inspire us, to push us forward in our quest for understanding. If they do exist, then they are the oldest and most fundamental structures in the entire universe, predating the formation of galaxies, of stars, and even of the first stable atoms. They are living, breathing fossils from a time before anything we would recognize as existence had even begun. And if they do not exist, then we are left with another, equally profound, mystery. What happened to the extreme, primordial density fluctuations that our theories predict should have formed them? Why did the early universe evolve in such a way that it so perfectly and so elegantly avoided their creation? Either way, whether they are out there in the darkness or not, the search for primordial black holes forces us to confront the very limits of what we can know, of what we can see, of what we can ever hope to understand. The universe is vast, and some of its deepest and most beautiful secrets may remain hidden from us forever, lost in the deep, profound, and eternal silence of space. The solar system that we see today, with its familiar and largely stable arrangement of planets and moons, is a product of billions of years of cosmic evolution. It is a system that has been shaped by violent collisions, by graceful planetary migrations, and by the relentless and patient pull of gravity. When we look up at the familiar, comforting face of our own moon in the night sky, or when we observe the beautiful, intricate dance of the moons of Jupiter and Saturn through our telescopes, we are only seeing a small and perhaps fortunate fraction of what once existed. The solar system was not always as it is now. It was once a far more chaotic, more dynamic, and more violent place, a place where countless, and now forgotten, moons were formed, only to be torn apart, to be ejected into the cold, deep space, or to be lost forever to the dark and silent void. These lost moons, these ghostly and often tragic remnants of a time when our solar system was still young, wild, and unstable, may still exist somewhere out there, hidden beyond the reach of our current instruments, drifting alone and silently in the eternal darkness. Some of them may have been completely destroyed in violent and cataclysmic impacts, their shattered remains now forming the rings of the giant planets or the scattered debris of the asteroid fields. Others may have been thrown out into the distant and largely unexplored reaches of the Oort cloud, a vast, spherical, and icy region that marks the very edge of our solar system. A place where they would remain frozen, undisturbed, and nearly impossible for us to ever detect. And some, the most unfortunate of all, may have escaped the gravitational pull of our sun entirely, becoming rogue moons, wandering aimlessly and eternally through the vast, cold, and lonely expanse of interstellar space, untethered from any star, and destined to drift forever in the endless silent night. In the earliest days of our solar system, more than 4.5 billion years ago, there were no clearly defined planets, no stable, predictable orbits, no familiar cosmic clockwork. Instead, there was a vast, swirling, and turbulent disk of gas, dust, and debris surrounding our young, and still forming, sun. And as this primordial material slowly began to clump together under the influence of gravity, the first infant planets, the protoplanets, and their first nascent moons began to form. But this was not a peaceful or a gentle process. It was a time of cosmic violence, a time of immense and often world-shattering collisions. Newly formed planets and moons were constantly smashing into each other, their surfaces being reshaped, their orbits being altered, or their very existence being snuffed out in a final, fiery instant. Some of these impacts were so powerful, so cataclysmic, that they changed the entire course of our solar system's history. The very moon that we see in our sky today is thought to have been formed from just such an event, a massive and glancing collision between the early molten Earth and a Mars-sized protoplanetary body. An impact that would have ejected a vast cloud of molten rock and debris into orbit, which then, over time, coalesced to form our familiar and beautiful lunar companion. And if this could happen to our own Earth, then it is almost certain that the other planets in our solar system also had a long and often violent history of moon formation, a history where moons were formed, were destroyed, and were replaced multiple times throughout the chaotic youth of our cosmic neighborhood. The giant, gas planets of our outer solar system, Jupiter and Saturn, have dozens of moons today, a beautiful and complex family of orbiting worlds. But in the distant past, they may have had even more. These gas giants are so incredibly massive that they have a powerful gravitational reach, an ability to capture passing objects and to pull them into orbit. This means that many of their current moons were likely not formed alongside them, but were stolen from the asteroid belt, or were captured from the icy debris of the outer solar system. But just as these giant planets can capture new moons, they can also lose their old ones. When planets migrate, when they slowly shift their positions in the solar system due to the complex gravitational interactions between them, they can disrupt everything around them. A moon that was once in a safe and stable orbit can suddenly find itself on a new and highly elliptical path, a path that could lead it to collide with another moon, to crash into its host planet, or to be flung with immense force out of the planetary system entirely. Jupiter and Saturn, our solar system's two gravitational behemoths, likely underwent significant periods of migration in their early histories. A chaotic cosmic dance that would have reshaped the entire architecture of the outer solar system, and would have, in all likelihood, resulted in many of their original primordial moons being lost in the process. Some of these lost, ancient moons may still be out there, hiding in the farthest and coldest reaches of our solar system, far beyond the orbit of Neptune, beyond the Kuiper Belt, in the vast and largely mysterious realm of the Oort cloud. The Oort cloud is a hypothetical and almost unimaginably large, spherical cloud of icy bodies that is thought to surround our solar system, at a distance of nearly a light-year from the Sun. It is believed to be the ancient and largely undisturbed reservoir of long-period comets, those icy and beautiful visitors that occasionally get nudged from their distant orbits and fall inwards towards the sun, their long, ghostly tails a fleeting and beautiful reminder of the vast, cold, and ancient history of our cosmic home. And if these smaller, icy bodies, these comets, can survive in the Oort cloud for billions of years, then it is entirely possible that some of our solar system's lost, ancient moons also ended up there, trapped forever in the faint, gravitational influence of our sun, but too far away, too cold, and too dark for us to ever see them. These would be frozen and lifeless worlds, locked in the deep, silent space of the outer solar system, their surfaces preserving a perfect and eternally unchanging record of the violent and chaotic youth of our cosmic neighborhood. And even if they do exist, finding them would be a task of almost unimaginable difficulty. They would be too dark and too distant to be observed directly with any of our current or even near-future telescopes. Other, and perhaps more numerous, of these lost moons may have faced an even more dramatic and more final, fate complete, and total ejection from the solar system itself. If a moon, during a close gravitational encounter with a massive planet, was thrown outwards with enough force, with enough velocity, it could have escaped the gravitational pull of our sun entirely, becoming a rogue object, a lonely and untethered wanderer, drifting freely and silently through the vast, dark, and empty expanse of interstellar space. Scientists in recent years have already discovered the existence of rogue planets, planets that do not orbit any star, but instead move, dark and alone, through the galaxy. And if rogue planets exist, then it is almost certain that rogue moons must also exist. Some of them may have been born in the turbulent, star-forming nurseries of our galaxy, but many of them, perhaps even billions of them, may have once been a part of a solar system just like our own, a moon that was torn from its home by the chaotic, gravitational dance of its planetary siblings. And some of them, it is almost certain, may have once been our own, forgotten and long lost, cosmic neighbors, without a nearby star to warm them, to illuminate them. These lost, rogue moons would be almost completely invisible, impossible to detect with even our most advanced and most powerful telescopes. They could pass by other solar systems, moving silently and darkly through the void, never to be captured by the gravity of another planet, forever alone in the endless cosmic night. And if any of these moons once had the potential for life, if they had subsurface oceans of liquid water, or the right chemical ingredients for biology, their ejection into the cold, deep space would have sealed their fate. Without the gentle, life-giving warmth of a star, any potential for life would have been frozen in an instant, preserved forever in the deep, icy shell of a moon that would never again see the light of day. The thought of such worlds, of places that once held the potential for oceans, for weather, for dynamic, geological activity, now drifting, dark and aimlessly, through the vast and lonely void, is a profound and deeply haunting reminder of just how fragile and how precious celestial bodies can be. Unlike the massive planets, which have a strong and stable gravitational hold on their orbits, the smaller moons are far more easily lost, making them some of the most transient and most vulnerable objects in the entire universe. The lost moons of our early solar system are not just a romantic and tragic relic of our cosmic past. They are also a crucial and largely missing piece of the puzzle of how planetary systems form and evolve. By studying the moons that remain, the ones that have survived the long and often violent history of our solar system, scientists can begin to infer what might have happened to those that were lost. The deep, ancient craters on our own moon, the irregular and often chaotic shapes of the asteroid belts, the strange and highly inclined orbits of the small, icy bodies in the outer solar system. All of these are clues, are fossils, that point to a history that is far more violent and far more complex than the serene and seemingly peaceful solar system we see today. If we ever develop the technology to send spacecraft on long, multi-generational journeys to explore the vast and largely unknown reaches of the Oort cloud, we may one day find direct and stunning evidence of these lost ancient moons. Perhaps we will even find the frozen and perfectly preserved remnants of worlds that were once a part of our own familiar cosmic neighborhood. But for now, these lost moons remain a deep and beautiful mystery, hidden forever beyond our reach. Some may still be orbiting, dark and unnoticed, in the vast, cold expanse of the outer solar system. Some may be buried, deep and forever, in the distant, icy graveyard of the Oort cloud. And many, many others have likely left us forever, drifting, dark and alone, in the endless, silent emptiness between the stars. We may never know their names, we may never see their shapes, we may never learn their stories, but they're silent and ghostly. Absence is a powerful and deeply poignant reminder of the profound and often tragic impermanence of celestial bodies, a reminder of the way that the cosmos is constantly shifting, constantly changing, and constantly reshaping itself in a beautiful and often violent and eternal cosmic dance. The universe is full of forgotten worlds, and among them, silent and unseen, are the lost, lonely moons of our own, ancient past, silent travelers, forever unremembered, but forever a part of the grand and ongoing story of our solar system. The universe is in constant and often dramatic motion. It is a vast and dynamic expanse, a place where entire galaxies, each containing hundreds of billions of stars, are not just floating aimlessly in the void, but are drifting and often racing through space, bound together by the invisible and powerful threads of gravity. Our own Milky Way galaxy, along with its retinue of smaller satellite galaxies, is not a static island universe. It is part of a much larger cosmic flow, a grand celestial river of galaxies that is being pulled with immense and inexorable force towards something massive, something mysterious, something that we cannot even directly see. This unseen and incredibly powerful gravitational force is known as the Great Attractor, a vast and diffuse gravitational anomaly that is so powerful, so massive, that it is drawing entire clusters of galaxies, including our own, towards it at almost unimaginable speeds. And yet, for all of its profound and universe-shaping influence, we cannot see it. The Great Attractor lies hidden, shrouded, and tantalizingly behind the thick and obscuring veil of our own galaxy's dusty, star-filled plain, a region of the sky known as the zone of avoidance, making it one of the greatest and most frustrating mysteries in all of modern cosmology. To understand the true significance and the deep mystery of the Great Attractor, we must first zoom out and look at the large-scale structure of the universe itself. Galaxies are not scattered randomly and uniformly throughout space. Instead, they are arranged in a vast and beautiful cosmic web, a network of immense, interconnected filaments of galaxies surrounding vast and largely empty cosmic voids. Our own Milky Way is a member of a small and relatively modest collection of about 50 galaxies known as the Local Group. And this local group is itself just a small suburban outpost on the edge of a much, much larger structure, a massive supercluster of galaxies known as the Laniakea supercluster. This cosmic behemoth, whose name means immeasurable heaven in Hawaiian, contains over 100,000 galaxies, all gravitationally bound and all moving, more or less, in the same general direction through space. And that direction, as astronomers have painstakingly discovered by measuring the subtle motions of thousands of galaxies, is directly towards the mysterious and unseen Great Attractor. The gravitational pull of the Great Attractor is enormous. Our own galaxy, the Milky Way, is being pulled towards it at a staggering speed of about 600 kilometers per second, which is over 1.3 million miles per hour. And everything else in our cosmic neighborhood, including the entire massive Virgo cluster of galaxies and all the other nearby galaxy groups, is also moving in the same general direction, all caught in the same powerful gravitational current. This coherent, large-scale flow of galaxies strongly suggests the presence of an immense and previously unknown concentration of mass, a mass that is far, far larger than anything in our immediate cosmic vicinity. And yet, when astronomers have tried to pinpoint the source of this immense gravitational pull, they have run into a formidable and deeply frustrating problem. The center of this gravitational anomaly is located in a part of the sky that is almost completely obscured by the dense and intervening clouds of gas, dust, and stars of our own Milky Way's galactic plane. This region, the zone of avoidance, acts like a thick cosmic fog, blocking our view and making direct optical observations of what lies beyond it almost completely impossible. For decades, scientists have struggled to understand what lies behind this cosmic barrier. If the Great Attractor is so incredibly massive that it can influence the motion of entire superclusters of galaxies, then why can we not see it? The answer, it seems, lies in the way that mass is distributed in the universe, unlike a single, compact object, like a supermassive black hole or a dense, collapsed star. The Great Attractor is not a single, well-defined body. It is, instead, a vast and highly diffuse region of space, a place where the density of galaxies and of the invisible dark matter that surrounds them is particularly high. It is the combined and immense gravitational pull of all these individual and often faint structures that creates the powerful and large-scale gravitational attraction that we observe. But because this mass is spread out over such a vast and distant region of space, it does not emit a single concentrated point of light, like a bright star or a quasar would, making it even more difficult to detect and to study. Despite these immense challenges, astronomers, with their characteristic ingenuity and perseverance, have found clever and indirect ways to study the Great Attractor. By using radio waves and X-ray telescopes, which can penetrate through the obscuring dust and gas of the Milky Way's plane far more effectively than visible light, scientists have been able to detect some of the galaxies and galaxy clusters that reside within this hidden cosmic region. And these observations have revealed a tantalizing and even more complex picture. They suggest that the Great Attractor itself is not the final, ultimate source of the gravitational pull, but is, in fact, just one part of an even larger and even more massive structure, a colossal supercluster of galaxies known as the Shapley supercluster. The Shapley supercluster is one of the most massive and most densely populated concentrations of galaxies in the entire observable universe. It contains thousands of individual galaxies, all packed together in a relatively small volume of space, and it is now thought to be the true primary source of the immense gravitational pull that is affecting our entire local region of the cosmos. But the mystery does not end there. Even beyond the immense gravitational influence of the Shapley supercluster. Astronomers have found evidence that our entire local supercluster, Laniakea, is being influenced by another, even more distant and even more powerful cosmic force. This has led to the discovery of what is known as the dipole repeller, a vast and largely empty cosmic void that is, in effect, pushing us away. While the Great Attractor and the Shapley supercluster are pulling us forward, the cosmic motion of our galaxy, it seems, is the result of a complex gravitational tug-of-war, a delicate and beautiful dance between the immense, attractive forces of the great cosmic structures on one side and the subtle, repulsive forces of the great cosmic voids on the other. This suggests that the universe is shaped by even larger and even more complex forces than we had ever imagined, forces that extend far beyond what we can currently, and perhaps ever, directly observe. One of the most intriguing and most important aspects of the mystery of the Great Attractor is the central and largely unknown role of dark matter. The ordinary baryonic matter that makes up the stars, the planets, the gas, and the dust that we can see accounts for only a small and almost insignificant fraction of the universe's total mass. The vast majority of the matter in the cosmos, about 85% of it, is composed of a mysterious and completely invisible substance that we call dark matter. We know it is there because we can see its immense gravitational effects. But we do not know what it is, and it is entirely possible, and even likely, that the immense gravitational pull of the Great Attractor is not just the result of the visible baryonic galaxies that we can, with great difficulty, detect within the zone of avoidance. It is also, and perhaps primarily, the result of a vast and completely unseen concentration of this mysterious dark matter. If this is the case, then our inability to directly and clearly observe the Great Attractor is not just due to the obscuring fog of our own Milky Way, but also, and more fundamentally, because the vast majority of its mass is made up of a strange and invisible substance that we still do not fully understand. As our technology continues to advance, astronomers are developing new and ever more powerful ways to peer into the hidden and forbidden corners of our universe, new and more sensitive. Infrared and radio telescopes are continuing to provide us with clearer and more detailed glimpses of the galaxies that lie within the zone of avoidance and future. Next-generation space missions may offer even deeper and more profound insights. The Vera C. Rubin Observatory, a massive new telescope that is set to begin its survey of the southern sky in the coming years, will provide an unprecedented and wide-field map of the universe, and it may uncover new and crucial clues about the nature of the Great Attractor and its place in the grand cosmic structure. Similarly, the successors to the James Webb Space Telescope could help us to refine our understanding of this profound gravitational enigma. But for now, the Great Attractor remains one of the most intriguing, most elusive, and most beautiful of all cosmic mysteries. We know it is there. We can feel its inexorable gravitational pull, and yet we cannot fully or clearly see it. It is a powerful and deeply humbling reminder that despite all the remarkable and often stunning progress we have made in our quest to understand the universe, there are still vast and powerful forces that are shaping our cosmic destiny, forces that remain, for now, completely hidden from our view. Perhaps one day, with the right new tools and with the right new theoretical insights, we will finally be able to unveil the true and full nature of the Great Attractor and to understand its central and profound place in the grand and beautiful structure of the cosmos. But until then, we continue to race towards it at over 1,000,000 miles per hour, bound by the silent and invisible threads of gravity that so beautifully and so mysteriously weave our entire universe together. In the vast and often bizarre menagerie of the cosmos, among all the strange and wonderful particles that make up our reality, there are some that are so elusive, so ghostly, so profoundly interactive, that they can pass through entire planets, through stars, through galaxies, without ever leaving a single detectable trace. These are the neutrinos, the little neutral ones, the shyest and most mysterious of all the known fundamental particles. But there may be an even stranger and even more elusive version of these particles, a hypothetical entity that is so undetectable, so intangible, so completely and utterly disconnected from our familiar physical world that it could be all around us, passing through us and shaping the very evolution of our universe, without us ever being able to directly know it. These are the sterile neutrinos, the true and ultimate ghost particles of the universe. And if they exist, they may hold the key to some of the deepest and most profound mysteries in all of modern physics. To understand the strange and wonderful nature of sterile neutrinos, we must first look at their more familiar and already quite strange relatives, the three known flavors of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. These neutrinos are produced in incredible abundance throughout the entire universe, emerging from the fiery nuclear reactions in the hearts of stars, from the cataclysmic, explosive deaths of supernova, and even from the decay of radioactive elements here on Earth. Every single second, trillions upon trillions of neutrinos, mostly from our own sun, are passing through your body without you ever noticing, without them ever leaving a single discernible trace. This is because neutrinos interact with other matter only through the weak nuclear force, one of the four fundamental forces of nature, and this force, as its name suggests, is incredibly weak. A neutrino could travel through a light year of solid lead without ever hitting a single atom. And yet, for all their near invisibility, physicists, with their characteristic ingenuity, have been able to detect and to study these neutrinos. They have built giant and often beautiful underground detectors, massive tanks filled with thousands of tons of ultra-pure water or liquid argon, buried deep beneath mountains to shield them from the confusing noise of other, more interactive, cosmic rays. And in these vast, silent chambers, the rarest of the rare, quantum interactions between a neutrino and an atom can be detected, leaving behind a faint and beautiful trace of its ghostly passage. But sterile neutrinos, if they exist, would be something else entirely. Unlike the three known types of neutrinos, which all participate in the weak nuclear force, sterile neutrinos are theorized to not interact with ordinary matter at all, not even through this incredibly weak force. The only influence they would have on the universe would be through the universal and all-pervasive force of gravity. This means that even our most advanced and most sensitive neutrino detectors would be completely and utterly blind to them. If sterile neutrinos exist, they could be the most elusive and most mysterious form of matter in the entire universe, hidden from us in plain sight. Their presence felt only through the subtle and often ambiguous pull of their collective gravitational weight. The idea of the sterile neutrino, as strange as it may sound, is not just a wild, ad hoc speculation. It arises naturally from several deep and as yet unresolved mysteries in our current understanding of physics. One of the biggest of these puzzles is the very fact that neutrinos have mass at all. In the standard model of particle physics, the incredibly successful theory that describes all the known fundamental particles and their interactions. Neutrinos were originally thought to be completely massless, like the photon, but a series of brilliant and Nobel Prize-winning experiments in the late 1990s and early 2000s showed that neutrinos do, in fact, have a tiny, but non-zero, mass. This was a revolutionary discovery, as it was the first direct experimental evidence for physics beyond the Standard Model. And one of the most elegant and most popular theoretical explanations for the origin of neutrino mass is the seesaw mechanism, a model that requires the existence of a new and much heavier type of neutrino that does not interact through the weak force. This would be the sterile neutrino, another and more direct clue that points to the possible existence of sterile neutrinos comes from a series of strange and still unexplained anomalies in the data from several different neutrino experiments. Experiments like the liquid scintillator neutrino detector at Los Alamos in the 1990s and the more recent Mini-Boone experiment at Fermilab have observed an excess of certain types of neutrino oscillations, the process by which neutrinos can change their flavor as they travel through space that cannot be easily explained by the three known types of neutrinos alone. One possible and very exciting explanation for these anomalies is that there is a fourth, and as yet undiscovered, type of neutrino, a sterile neutrino that is mixing with the other three, creating a new and more complex pattern of oscillations. And if sterile neutrinos exist, they could also help to solve one of the greatest and most enduring mysteries in all of cosmology, the nature of dark matter. Dark matter, as we have seen, is the invisible gravitational substance that makes up about 27% of the total mass energy content of the universe. We know it is there, but we do not know what it is. Some theories propose that sterile neutrinos, if they have the right mass, could be a form of warm dark matter, a candidate that could explain some of the subtle discrepancies between the predictions of the standard cold dark matter model and the observed structure of galaxies on small scales. If this is the case, then the universe is filled with a vast and ghostly sea of these sterile neutrinos, their collective gravity shaping the evolution of the cosmos, while they themselves remain almost completely and utterly undetectable. The challenge, of course, the great and deeply frustrating challenge, is to find a way to prove that these ghostly sterile neutrinos actually exist, because they do not participate in the weak nuclear force. Our current direct detection methods are completely useless, so scientists have been forced to get creative, to look for the subtle, indirect signatures of their existence. The search for anomalous neutrino oscillations continues, with new and more powerful experiments, like the Deep Underground Neutrino experiment, which will send a beam of neutrinos 800 miles through the Earth from Fermilab in Illinois to a massive underground detector in South Dakota, hoping to measure the properties of neutrino oscillations with unprecedented precision. Other experiments are looking for the faint, X-ray signals that could be produced by the very slow decay of sterile neutrinos over cosmological timescales. And some are even looking for the subtle, gravitational effects that a large population of sterile neutrinos could have on the structure of the early universe, as seen in the faint, ancient light of the cosmic microwave background. But so far, no definitive and universally accepted evidence has been found. The implications of discovering a sterile neutrino would be truly enormous. It would not just force us to rewrite the textbooks of particle physics, it could also fundamentally reshape our understanding of the universe's composition, its history, and its evolution. It might even provide a crucial clue to another deep and related mystery, the matter-antimatter asymmetry of the universe. According to our current understanding of physics, the Big Bang should have produced matter and antimatter in almost exactly equal amounts, and when matter and antimatter meet, they annihilate each other in a flash of pure energy. So, the universe should be filled with nothing but a sea of radiation. But it is not. It is filled with matter, with us. Something, in the first, fiery moments of creation, must have tipped the cosmic scales, creating a tiny but crucial excess of matter over antimatter. The leptogenesis scenario, a leading theoretical explanation for this asymmetry, proposes that the decay of heavy, sterile neutrinos in the early universe could have created this imbalance, a process that is intimately linked to the same seesaw mechanism that gives the light neutrinos their mass. But what if sterile neutrinos are never found? What if they exist, but are truly and fundamentally undetectable? They would remain forever beyond our reach, a ghostly and unprovable presence, their influence on the cosmos felt, but never directly seen. This would be one of the most frustrating and most humbling possibilities in all of physics. A fundamental and perhaps even crucial particle that shapes the very nature of our reality. But that can never be conclusively and definitively proven to exist. It would be like knowing that there is a hidden and powerful force that controls the destiny of the universe, but never being able to touch it, to see it, or to measure it in any way. And yet, the history of science has shown us, again and again, that what seems undetectable today may become observable with the new and often unpredictable technologies of the future. When the neutrino itself was first theorized by Wolfgang Pauli in the 1930s, many physicists, including Pauli himself, believed that it would never be detected, as it was thought to interact far too weakly with matter. But decades later, clever and patient, experimentalists built the giant underground detectors that proved that neutrinos were real. Perhaps one day, a new and even more clever breakthrough in physics will allow us to indirectly but unambiguously confirm the existence of sterile neutrinos, unlocking one of the final and most profound secrets of the cosmos. But until then, sterile neutrinos will remain a beautiful and deeply tantalizing possibility, a ghostly whisper in the grand cosmic symphony, a silent and powerful force that may exist forever, just beyond our grasp, whether they are the key to the mystery of dark matter, the answer to the puzzle of cosmic asymmetry, or merely a phantom, a beautiful and ultimately incorrect prediction that will lead us in new and even more interesting directions. They're profound and beautiful. Mystery continues to haunt the very frontiers of modern physics. For as long as humans have gazed up at the night sky, for as long as we have been conscious, questioning beings, we have wondered where everything came from. The prevailing and remarkably successful scientific theory is that our universe began approximately 13.8 billion years ago, in a hot, dense, and incredibly energetic event that we call the Big Bang. Everything we see today, the stars, the galaxies, the planets, and even the very fabric of space and time itself was born from this single, momentous, and transformative moment of creation. But this powerful and well-tested explanation inevitably raises a deeper and perhaps even more profound question: what came before the Big Bang? Was there a time before time? Did our universe simply and miraculously emerge from a state of absolute nothingness? Or has the universe, in some strange and perhaps unrecognizable form, always existed? And if it has, are all the past, and perhaps infinite, versions of our reality lost to us forever? Their histories, their stories, their very existence erased like fleeting, ephemeral footprints on a vast and timeless cosmic shore. One of the most perplexing and most humbling ideas in all of modern physics is that the very concept of time itself may have begun with the Big Bang. According to Einstein's general theory of relativity, space and time are not separate, independent entities. They are two inseparable aspects of a single, unified, four-dimensional fabric that we call space-time. And if the universe, if space, had a beginning, then it seems that time itself must have also had a beginning. This means that asking the question, what came before to the Big Bang, might be like asking the question, what is north of the North Pole? It may be a question that is not just unanswerable, but is, in a fundamental, logical sense, meaningless. However, many physicists and many philosophers are not satisfied with this seemingly simple and somewhat dismissive answer. If the universe and time itself simply sprang into existence from nothing, then what determined the specific laws of physics that govern it? Why does the universe exist at all, with all its beauty and its complexity, instead of simply remaining in a state of eternal, empty, and timeless void? These deep and perhaps unanswerable questions have led scientists to explore other, more exotic and more mind-bending possibilities, including the idea that the universe is, in fact, eternal, and has always existed in some strange and cyclical form. One of the most popular and most elegant of these alternative theories is the idea of a cyclic universe. Instead of beginning from a state of absolute and singular nothingness, the universe may go through an endless and perhaps eternal series of expansions and contractions, much like a great cosmic heartbeat. In this model, the Big Bang was not the true, absolute beginning of all things, but was merely the latest rebirth of the universe, before our current expanding universe. There may have been another, and perhaps very different, universe. A universe that expanded, that cooled, that formed its own stars and galaxies, and that then, eventually, collapsed back in on itself in a fiery, big crunch. A cataclysmic event that then, in turn, gave rise to the Big Bang of our own cosmic eon. And if this process has been happening forever, then the universe has no true, single starting point. It has only an endless and beautiful cycle of creation and destruction, of death and rebirth. But if the universe is truly cyclical, if it has gone through a potentially infinite number of past iterations, then what happened to all of those previous universes? Why do we have no memory, no record, no physical evidence of their existence? The answer, it seems, may lie in the relentless and unforgiving arrow of time, the second law of thermodynamics. With each new cycle of the universe, the total entropy, the total amount of disorder, should increase. This means that even if a new universe is born from the ashes of the old, it will not be an exact copy. The information from the previous cycle, the detailed record of its history, its structure, its life, is effectively lost, scrambled, and erased in the fiery and high entropy crucible of the bounce from a big crunch to a big bang. This means that even if there have been an infinite number of past universes, they have each, in their own turn, left no discernible and recoverable trace behind. Everything that came before us in this cyclic picture has been effectively and completely erased, making it impossible for us to ever recover any direct and detailed knowledge of what happened before our own local Big Bang. Another, and equally profound, possibility is the idea of the multiverse. Instead of a single universe that cycles through different sequential stages, there may be an infinite and coexisting number of other parallel universes, each with its own unique beginning, its own unique history, and its own unique set of physical laws. In some versions of this theory, like the eternal inflation model, new bubble universes are constantly being born in a vast and ever-expanding cosmic landscape, each one emerging from a random quantum fluctuation or from a localized, phase transition-like expansion of space-time. If this is true, then what came before our own Big Bang was not a single previous universe, but a vast and complex multiversal reality, a cosmic foam where every possible and conceivable reality exists somewhere in its own self-contained bubble. But even the multiverse does not fully or satisfyingly answer the question of an infinite past. If there are many, and perhaps an infinite number of other universes, then where did they come from? Has the multiverse itself always existed, or did it, too, have a beginning? Some scientists and philosophers have proposed that the very concept of time itself may not be a fundamental aspect of reality, that what we experience as the linear to forward flow of time is just a human, and ultimately illusory, perception of a much deeper and perhaps timeless reality. If time is an emergent property rather than a fundamental feature of the universe, then the very question of what came before the Big Bang may not have a meaningful or even a sensible answer at all. The universe, in this sense, may simply be a timeless and eternal mathematical structure without a beginning or an end. However, there is one formidable and perhaps insurmountable problem that remains, regardless of which of these grand cosmological stories we choose to believe, and that is the nature of the Big Bang itself. If we could somehow, with our theories and our instruments, peer back far enough into the past, beyond even the first fleeting moments of our universe's existence, we might be able to find some direct and unambiguous clues about what came before. But the problem is that our current and remarkably successful physical theories, the theories of general relativity and quantum mechanics, break down at the very moment of the Big Bang. The extreme and infinite density and energy of the early universe create a singularity, a point in space-time where our laws of physics cease to have any meaning, where our equations give nonsensical, infinite answers. This singularity acts like a great and impenetrable cosmic curtain, blocking us from ever being able to see or to know anything that lies beyond it, unless we can somehow develop a new and more complete theory of physics, a theory of quantum gravity that can describe what happens at and beyond the singularity. The ultimate past, the time before the Big Bang, may forever remain a deep and beautiful mystery, despite these immense and perhaps even fundamental challenges. Some scientists believe that we may still be able to find some indirect and circumstantial evidence of a time before the Big Bang. If the universe is truly cyclical, there might be subtle and almost imperceptible imprints of the previous universes left behind in the faint, ancient glow of the cosmic microwave background. Some researchers have suggested that certain large-scale circular patterns in the temperature of this radiation could be the ghostly and beautiful remnants of the black hole collisions that occurred in the previous cosmic eon. So far, no such conclusive evidence has been found. Similarly, if the multiverse is real, then the collision of our own bubble universe with another could have left a cosmic bruise, a subtle and detectable distortion in the distribution of galaxies on the largest scales. But what if we will never, ever truly know the answer? What if the past is, in fact, lost to us forever, hidden behind an impenetrable and eternal wall of cosmic history. If that is the case, then the true nature of the infinite past may remain one of the greatest and most beautiful of all unanswered questions in science. We may live in a universe that, by its very nature, erases its own history. A universe that is constantly being reborn. A universe that leaves us with only the fleeting and beautiful present moment, and a deep and enduring mystery that stretches forever and silently into the endless and unknowable past. And still, the search for answers continues. Every new discovery, every new theory, brings us just a little bit closer to understanding the true and ultimate origins of our own cosmic reality. And perhaps one day, a new and brilliant breakthrough in physics will reveal a deeper and more profound truth about the nature of space, of time, and of existence itself. But until then, we are left to wonder, was there something before the Big Bang? Or has the universe, in some strange and beautiful and perhaps cyclical form, always been stretching back forever into an infinite and timeless past that we can never, ever truly grasp? The search for intelligent life beyond our own small and fragile planet is a question that has haunted the human imagination for centuries. With an estimated 2 trillion galaxies in our observable universe, each filled with hundreds of billions of stars, and with the recent discovery of countless and often Earth-like planets orbiting those stars, it seems almost a statistical impossibility that we are alone. The sheer, overwhelming numbers suggest that life, and perhaps even intelligent and technological life, should have arisen many, many times throughout the long and often violent history of the cosmos. And yet, when we turn our radio telescopes to the heavens, when we listen for the faint and telltale whispers of a distant alien civilization, the universe is eerily and profoundly silent. We have been listening with ever-increasing sensitivity for decades now, scanning the vast and seemingly empty expanse of the sky for any sign, for any signal, for any single anomalous blip that would tell us that we are not alone. But we hear nothing. If intelligent life is truly a common and perhaps even an inevitable outcome of the laws of physics and biology, then where is everyone? This is the simple and deeply unsettling question at the heart of the Fermi paradox, a paradox that pits the high statistical probability of extraterrestrial intelligence against the complete and deafening lack of any evidence for it. One of the most sober and most plausible possibilities is that other intelligent civilizations once existed, but are now long and tragically gone. The universe is ancient, more than 13.8 billion years old. This is an almost unimaginable expanse of time, a time scale upon which entire species, entire civilizations, entire biospheres could have evolved, could have flourished, and could have vanished. Millions or even billions of years before human beings ever walked the earth. If alien civilizations rose and fell long before we ever developed the technology to detect them, then we have, in a cosmic sense, simply missed them, their messages, their probes, their great interstellar broadcasts, if they ever sent any, may have passed through our small corner of the galaxy thousands or even millions of years ago, long before we had the means or the inclination to listen. Or worse, their signals might still be on their way, a faint and lonely whisper from a long-dead civilization. A message in a bottle that will only arrive at our shores long after our own. Human civilization has itself ceased to exist. This idea that civilizations do not last is a troubling but powerful answer to the Fermi paradox. It suggests that the cosmos may be filled not with thriving, interstellar empires, but with the silent and ghostly remnants of once great civilizations, with dead and barren worlds where advanced and perhaps even beautiful beings once lived but are now reduced to a final and eternal silence. There are many, and often terrifying, possible reasons why intelligent and technological civilizations might not endure for very long on a cosmic time scale. One of the most widely and most anxiously discussed of these ideas is the concept of the Great Filter, a hypothetical and seemingly insurmountable barrier that prevents most, if not all, civilizations from ever advancing beyond a certain critical stage. If this filter lies in our past, then it would mean that the emergence of life, or of intelligence, or of technology, is an incredibly and almost miraculously rare event, and that we, as a species, are one of the first and perhaps the only intelligent beings to have ever reached this point in our galaxy. But if the filter lies in our future, then it suggests a far more ominous and far more chilling possibility that all, or nearly all, advanced civilizations, like our own, inevitably, and perhaps even predictably, destroy themselves before they ever reach the level of stable, long-term, interstellar expansion. The ways in which a civilization might self-destruct are numerous, and all too familiar to us. Nuclear war is an obvious and terrifying possibility. A species that develops the incredible and almost godlike power to split the atom gains access to a source of almost limitless energy. But it also, and at the very same time, gains the ability to wipe itself out in a final and fiery instant. If alien civilizations had the same, and often self-destructive, political and social structures as our own, then they may have been just as prone to conflict, to tribalism, to war, and a war fought with weapons far beyond our current, and already terrifying. Technology could have left their entire home planets uninhabitable, extinguishing the bright and precious flame of intelligent life before it ever had the chance to spread beyond its own fragile and war-torn world, another and perhaps even more insidious possibility is environmental collapse, a highly advanced and highly successful technological civilization may, like our own, become deeply and perhaps fatally dependent on the finite resources of its home planet, consuming them at an ever-increasing and ultimately unsustainable rate. If they fail to manage their own technological success, if they fail to transition to a more sustainable and more harmonious way of life, they may have depleted their own ecosystems, they may have poisoned their own atmospheres, they may have altered their own climates beyond the point of recovery. Rising temperatures, failing crops, collapsing biospheres, these could have doomed them, leaving their once thriving and once beautiful worlds barren, silent, and dead. If civilizations repeatedly and predictably destroy their own planetary homes before they ever develop the means to leave them, then the galaxy could be filled with a vast and tragic graveyard of dead worlds. Worlds that once hosted the bright and fleeting promise of intelligent life. And then there are the biological threats. A civilization that advances to the point of being able to manipulate its own genetic code to master the arts of genetic engineering and synthetic biology might also, and perhaps inevitably, create diseases that it cannot control. Pandemics, whether natural or artificial, could have swept through their populations, wiping them out in a matter of years. And if intelligent beings experimented with altering their own biological nature, perhaps in the noble pursuit of immortality or of enhanced intelligence, or of a new and more perfect form of artificial evolution. They may have, with the best of intentions, unintentionally engineered their own and final downfalls. But what if civilizations do not destroy themselves intentionally? Some may have simply been the victims of a cruel and indifferent cosmic chance. They may have fallen victim to the many, and often unpredictable, external threats that the universe can throw at a fragile and planetary biosphere. A massive and civilization-ending asteroid impact, a supervolcanic eruption that plunges their world into a long and deadly volcanic winter. A nearby and powerful gamma-ray burst, the focused and incredibly energetic beam of radiation from a collapsing, massive star that could have sterilized their entire planet in a single, silent flash. Even if a civilization became a spacefaring one, even if they had managed to establish outposts on other planets or moons in their own solar system, they may still have been caught in the path of a truly and unimaginably catastrophic cosmic event. A rogue and wandering black hole, a close and violent collision between two stars, a nearby and powerful supernova explosion, if their entire long-term survival depended on the stability of a single and ultimately fragile planetary, or even a single star system. Then the destruction of their home could have meant the final and absolute end of their entire and perhaps billion-year-long species. There is also the even more unsettling and more paranoid possibility that some civilizations were not alone, but that they encountered others who did not have peaceful or even collaborative intentions. If intelligent and technological, species are, by their very nature, competitive and expansionist, then the first civilization to develop the means of interstellar travel might have, as a matter of cold and ruthless logic, viewed any other emerging civilizations as a potential future threat, a threat to be monitored and perhaps to be eliminated. This is the dark and chilling logic of the dark forest hypothesis, a possible solution to the Fermi paradox that suggests that advanced civilizations remain silent, not because they do not exist, but because they are terrified of attracting the attention of others. If every advanced species assumes that any other species might be hostile, then the safest and most logical course of action is to remain completely and utterly hidden. Those that have, in their naivety, revealed their presence, those that have broadcast their existence to the stars, may have been quickly and silently destroyed. Their bright and hopeful signals a final and tragic beacon that led to their own swift and merciless extinction. If this is true, then the universe might not be empty at all. It might simply be full of a vast and silent population of terrified and hiding civilizations, each one listening and waiting in the dark. And even if some rare and perhaps very lucky civilizations manage to survive all of these immense and often self-inflicted threats, there is still the final and perhaps most profound issue of all, the issue of time itself. The universe operates on a timescale that is so vast, so deep, so almost unimaginably long, that it dwarfs the lifespan of even the most ancient and most stable of civilizations. If an alien civilization flourished 1 billion years ago, and if it lasted for 1 million or even 10 million years before it finally collapsed or disappeared, that would still be an unimaginably long and successful lifespan for a civilization. But in the grand 14 billion-year-long timeline of the cosmos, it would be nothing more than a fleeting and almost imperceptible moment. If civilizations emerge and then disappear on timescales that are separated by millions, or even billions, of years, then the likelihood of two independent, intelligent species existing at the same time and also being close enough in space to detect each other is incredibly, vanishingly low. We may have simply arrived too late to the cosmic party, or too early, but perhaps civilizations do not vanish in a final, fiery destruction. Perhaps, instead, they simply retreat. They retreat inward, asufficiently, and perhaps unimaginably. Advanced species may, at some point, simply abandon the messy, difficult, and often dangerous project of physical and interstellar exploration altogether. If their technology reaches the point where they can create perfect and completely immersive virtual worlds, if they can upload their consciousnesses into vast and powerful computational machines, they may have no need and no desire to continue to explore the physical and often disappointing universe. They could have transferred their entire collective existence into a new and more perfect digital space, leaving behind only the silent and empty, planets and the dark and rusting cities of their physical and now abandoned past. If this is the case, then the answer to the Fermi paradox is not that civilizations do not last, but that they evolve beyond what we can recognize, beyond what we can detect, beyond what we can even comprehend, the most haunting and most lonely possibility of all, however, is that we are, in fact, the first. That intelligent and technological, life is so incredibly and so miraculously rare that we are at this moment the only and the first conscious beings in our entire galaxy, and perhaps even in our entire observable universe, to have reached this particular and perhaps very dangerous stage of development. If this is true, then we are standing at a profound and deeply significant cosmic precipice, facing a choice that may have determined the fate of all those who came before us, if they ever existed at all. We have the potential, the incredible and beautiful potential, to become the first civilization to break free from the Great Filter, to survive our own technological adolescence, to expand beyond our own fragile planet, and to spread the light of life and of consciousness out into the vast and silent stars. But we also face the very same and very real dangers that may have doomed countless and now forgotten others. The silence of the cosmos in this light is not just a scientific mystery. It is a profound and deeply moving warning. If civilizations before us have, in their pride and their folly, destroyed themselves, then we must, with all our collective wisdom and our deepest humility, learn from their silent and tragic mistakes. And if the universe is truly and completely empty, then the great and sacred responsibility falls on us and on us alone, to ensure that the beautiful and precious experiment of intelligent life does not end here with humanity. We have the ability, the technology, the knowledge to shape our own future, to decide whether we will be just another lost and forgotten civilization, or the first, and perhaps the only, to endure. For now, we continue to search, we continue to listen for the faint and hopeful signals from a distant star. We continue to send our own small and fragile messages out into the vast and silent void. And we continue to hope that we are not too late or too early. Perhaps one day we will hear something, a whisper from a distant star, a faint and beautiful trace of a civilization that survived where others, perhaps, have failed. But until then, we are left with the great and profound silence. And we are left to wonder whether it is the silent and tragic echo of all those who came before us, or the deep and lonely absence of anyone at all. The ultimate fate of our universe is one of the most profound, most beautiful, and most unsettling mysteries in all of cosmology. We exist in a universe that we know had a definite and fiery beginning in the Big Bang. But what happens at the end? Will everything collapse back in on itself in a final cosmic inferno? Will it tear itself apart into a state of absolute and chaotic oblivion? Or will it simply and silently fade away into a cold, dark, and eternal nothingness? No matter which of these grand and often terrifying scenarios plays out, there will be a final and absolute horizon, a point in the far to distant future where no observer, no matter how advanced, no matter how patient, will ever be able to witness what comes next. The very end of the universe will not just be lost to us, it will be lost to all of existence itself. To understand the future, we must first look to the past and to the present. The universe, as we have seen, began with the Big Bang, a moment of almost unimaginable energy and expansion that marked the creation of space and time itself. And from that initial, singular moment, everything has been expanding outwards, forming the vast and beautiful tapestry of galaxies, of stars, of planets that we see today. But the force that first set the universe in motion, the force of expansion, has never stopped. For the first few billion years of cosmic history, the force of gravity, the mutual attractive pull of all the matter in the universe, acted as a powerful cosmic brake, slowing down the rate of this expansion. But then, about 5 billion years ago, something changed. A new and mysterious force, an invisible and repulsive energy that we call dark energy, began to win the cosmic tug of war. And today, we know that dark energy is not just winning, it is dominant. The universe is not just expanding, its expansion is accelerating, growing faster and faster with each passing moment. And as time goes on, the distant galaxies will continue to drift farther and farther apart. What we see in our night sky today, the beautiful and seemingly eternal spiral and elliptical galaxies, will look drastically different in the far distant future. Eventually, one by one, these entire and magnificent island universes will disappear from our view, slipping silently and irrevocably beyond our cosmic event horizon, their light forever unable to reach us again. This alone is a strange and deeply terrifying thought. One by one, the universe is erasing itself from our own local perspective. But the true and ultimate fate of our universe depends entirely on the nature and the future behavior of this strange and mysterious dark energy. And scientists have theorized several possible and often haunting endings to our cosmic story. One of the most dramatic and most violent of these possible endings is the Big Rip. If dark energy is not a constant, but is a form of phantom energy that grows stronger and more repulsive over time, then it will not just continue to push the distant galaxies apart, it will eventually begin to tear apart the very fabric of reality itself. First, the great clusters of galaxies, the largest gravitationally bound structures in the universe, will be dissolved, their constituent galaxies flung out into the expanding void. Then, as the repulsive force of the phantom energy continues to grow, it will overcome the gravity of the individual galaxies themselves, breaking them apart, and leaving their billions of stars stranded and alone in the darkness. As the end approaches, The force will become so strong that it will overcome the gravity that holds our own solar system together, tearing the planets from their orbits and leaving them to wander, dark and cold, through an increasingly and violently unstable reality. Eventually, in the final, fleeting moments of the cosmos, the force of the Big Rip will overcome the electromagnetic forces that hold the atoms themselves together. And then, finally, the strong nuclear force that binds the protons and the neutrons in the atomic nucleus. Everything, matter, space, and perhaps even time itself will be ripped apart at the most fundamental subatomic level. The universe will not just end, it will be violently and completely destroyed. Its every structure, at every scale, reduced to a shower of free and causally disconnected fundamental particles. But there is another, and perhaps even quieter and more haunting fate that may await us, the heat death, also known as the Big Freeze. In this scenario, the cosmic expansion, driven by a constant dark energy, continues, but at a steady and ever-accelerating rate. The universe will continue to spread all of its matter and energy out over an ever larger volume of space until nothing can ever interact with anything else again. The stars will slowly and one by one exhaust their nuclear fuel, their bright and beautiful flames flickering and dying out, leaving behind only the cold, dark, and silent remnants of white dwarfs, neutron stars, and black holes. The galaxies themselves will fade into an eternal darkness, and then, over immense and almost unimaginable timescales, even these last remaining structures will begin to decay. The protons themselves may, according to some theories, be unstable and will, over trillions upon trillions of years, slowly decay into a sea of lighter particles and radiation. And the black holes, the last and most massive structures in the universe, will slowly and silently evaporate, radiating away their mass energy through the subtle quantum process of Hawking radiation. In the end, after an almost infinite amount of time has passed, the universe will be a cold, dark, empty, and lifeless place. There will be no new stars being born. There will be no galaxies colliding. There will be no motion, no warmth, no change. The universe will not have exploded. It will not have collapsed. It will have simply and quietly stopped doing anything at all. This is, for many, the most haunting and most existentially terrifying of all possible endings. Not a fiery and dramatic cataclysm, but a slow, cold, and inevitable fading into an absolute and eternal nothingness. And the worst and most poignant part of this story is that no one will be left to witness it. If any far future civilizations manage to survive for these billions or even trillions of years, they will slowly and inexorably fade with the dying stars. The last conscious being in the entire universe will have no one to tell their story to, no one to hear their final and lonely words. When the very last usable source of energy in the cosmos is finally used up, existence itself, in all its beauty and its complexity, will go silent. But there is still one more possibility, one that offers the tiniest and perhaps most beautiful glimmer of hope. Some theories, as we have seen, suggest that the universe may be cyclical, that after it fades or after it rips apart, a new universe could be born from its ashes. If this is true, then the end is not truly the end, but is just the beginning of something new, a new chapter in an eternal cosmic story. However, Even in this hopeful and beautiful picture, our own universe, our own story, would still be lost. If a new universe is born, it will be completely and utterly disconnected from our own. There will be no way to remember what came before, no trace of the past that can be left behind. Our universe, with all its beauty, all its complexity, all its life, everything that we know, everything that we have ever been, will still be lost forever to the sands of an eternal and unforgiving time. No matter what happens, no matter which of these grand cosmic scenarios plays out, the final and ultimate horizon of our universe is a line that no one and no thing will ever be able to cross. The end will come, and there will be nothing left to see it. It is a thought that is both profoundly humbling and deeply and beautifully sad. The universe is a grand and glorious and ultimately tragic story, and we are living in its middle, and perhaps its most beautiful and most interesting chapter. And the very fact that we are here now to witness it, to understand it, to appreciate its fleeting and beautiful and often terrifying glory is a miracle that is almost too profound for words. The universe, in all its vast and often mysterious splendor, is an endless expanse of wonder, a cosmic ocean filled with secrets that stretch far beyond the limits of our current, and perhaps even our future, understanding. It is a reality that calls to us, that ignites our curiosity, that fuels our ambition, and that urges us to explore the great, and often terrifying, unknown. And yet, for all our dreams of reaching the stars, for all our technological ingenuity, for all our boundless human perseverance, there are places in this vast and beautiful cosmos that we will never be able to set foot in, realms that are so distant, so hidden, or so fundamentally and physically unreachable, that they will remain forever beyond our grasp. These are the forbidden zones of the universe, and no amount of technology, no future, scientific breakthrough, no amount of pure human will ever allow us to breach their silent and eternal boundaries. Some of these forbidden and often tragic places are being actively and constantly created right now as we speak, torn from our view by the relentless and ever-accelerating expansion of space itself. With each passing moment, entire and magnificent galaxies, each containing billions of stars and perhaps billions of planets, are racing away from us at speeds that are faster than the speed of light, carried along on the ever-growing and ever-stretching fabric of the cosmos. The deeper we look into space, the more we realize just how much of the universe is already, and forever, gone. Regions of the cosmos that were once in the distant and ancient past, within our causal reach, now exist beyond a point, beyond a horizon, that we can never, ever cross. Even if we could somehow, one day, develop the technology for engines that could propel us at the very speed of light itself, it would not be enough. The very space between us and these distant and now forbidden realms is expanding too fast for us to ever be able to catch up. And even much closer to home, in our own local cosmic neighborhood, the ultimate barriers of the universe are just as real and just as insurmountable. Black holes, the most enigmatic and most powerful objects in all of existence, hold deep and perhaps eternal secrets that we may never be able to uncover. Their event horizons are not just a physical boundary, they are a one-way and absolute door to oblivion. Anything that crosses this point of no return, no matter how advanced, no matter how powerful, no matter how resilient, will never be able to come back, not even light, the fastest thing in the universe, can escape their immense and unforgiving gravitational pull. And whatever information, whatever story, whatever reality falls inside is, for all practical purposes, effectively and completely erased from the universe as we know it. The very nature of space and of time within a black hole is a deep and profound mystery to us, and it is a mystery that may be, in its very essence, forever unknowable. If we could somehow send a probe, a robotic emissary, into one of these dark and silent abysses, its signals, its data, its final desperate messages would never be able to reach us. And if an astronaut, a brave and perhaps foolish explorer, were to venture too close, they would be stretched and crushed and torn apart into a stream of fundamental particles, their body, their mind, their story, all reduced to a final and silent nothingness, long before they could ever hope to tell us what they had found. The heart of a black hole is not just a forbidden zone, it is the ultimate and most absolute point of no return. And what about the true and ultimate beginning of everything? The very first fleeting moments after the Big Bang hold the answers to some of the deepest and most profound questions that humanity has ever asked, questions that could explain our entire and often mysterious existence, and yet they are locked away from us forever, behind a thick and impenetrable veil of physics that we cannot and may never be able to penetrate. The universe, in its extreme and fiery infancy, was so incredibly hot and so unimaginably dense that light itself, the very photons that carry information across the cosmos, was unable to travel freely. The early universe was an opaque and chaotic fog, and this means that no telescope, no matter how powerful, no matter how sophisticated, will ever be able to directly see what truly happened at the very start. The first and most crucial moments of time itself exist behind an eternal and insurmountable wall, a forbidden zone that is not in space, but in time. But perhaps the most unsettling and most humbling reality of all is not just that there are places and times that we can never reach, but that the number of these forbidden zones is constantly and inexorably growing every single second. New and previously accessible regions of space are drifting silently and forever beyond our ability to ever explore. The universe is expanding, and with it, the possibilities for our own human and cosmic exploration are, in a very real and very tragic sense, shrinking. 1 trillion years from now, there will come a time when our own familiar Milky Way galaxy is the only thing that is visible in the vast and dark night sky. Every other galaxy, every other island universe will have vanished forever, beyond our cosmic horizon, never to be seen again. Future civilizations, no matter how advanced, no matter how curious, will never even know of the vast and beautiful cosmos that we, in our own brief and precious moment of cosmic history, are still able to glimpse. To them, the universe will appear as a lonely and isolated island, a single, solitary galaxy in an infinite and seemingly empty void. And yet, despite knowing all of this, despite knowing that there are limits, that there are boundaries, that there are places we can never go, we continue to reach, we continue to wonder, we continue to dream, even if we can never set foot in these lost and forbidden places. Even if the universe has set certain and absolute limits that we can never, ever cross, Our desire, our insatiable and beautiful human desire to understand is limitless. And perhaps, in the end, that is what truly and most profoundly defines us. Not where we can go, but what we seek to know. The forbidden zones of the universe, the lost galaxies, the dark hearts of black holes, the silent and ancient beginning of time, may never be explored in person, but they will always and forever be explored in our minds, in our theories, in our stories, in our dreams, and in that sense, in the beautiful and often tragic and endlessly creative journey of the human imagination. The quest, the exploration, the adventure never, ever truly ends.